Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. In the beginning, there was silence. A silence deeper than night, softer than a held breath. Nothing moved, for nothing yet existed that could move. No stars, no galaxies, not even the whisper of a breeze in the dark. In this primordial stillness, before light and time and form, there was only a pregnant pause, an infinite calm awaiting a spark. And then, in that void, something happened. A flash, a burst of unimaginable brightness, and the silence was broken. The universe was born in an eruption of light and energy, a silent explosion that rang with no sound, yet carried the promise of everything to come. From that moment, space unfurled like a new scroll, stretching, expanding, filling with the first hot glow of creation. Still, there was no ear to hear, no eye to see. All was energy and plasma and the slow birth of matter. Yet, as the cosmos burgeoned outward, the silence remained underneath the cosmic symphony, like a bass note holding all melodies, the backdrop of the vast expanding space. Eons passed in wordless majesty. Stars kindled across the darkness, clustered into galaxies, swirled into patterns by gravity's gentle but inexorable hand. Great structures formed, filaments of galaxies and voids larger than anything we can truly imagine. In all of this grandeur, in all the furnace roar of stars and the collisions of galaxies, a profound silence still reigned. It was not an empty silence, but a pregnant one, the silence of a universe in the making, as yet without anyone to witness it. Nebulae blossomed like cosmic flowers, stars lived and died, forging heavy elements in their hearts and scattering them into the void. Planets coalesced around distant suns. Perhaps on countless worlds, oceans pooled and gentle winds blew under alien skies. But for ages, no voice broke the silence, no mind yet asked a question. On one tiny planet, orbiting an ordinary star in an ordinary galaxy, something miraculous stirred. Life. In warm, shallow seas, simple microbes began to live, multiply, and evolve. The silent universe had given rise to tiny living things that could sense and respond. They knew nothing of the larger cosmos, only the immediate instinct to survive. But life grew more complex and daring. It crept onto land, took on myriad forms in oceans and forests. And in time, on that little blue world, consciousness sparked. Creatures emerged who could wonder. They looked up at the night sky with curious eyes. They felt small under the canopy of stars, yet compelled to reach out in thought. From their lips and hearts came the first question: what is all this? Where did it come from, and why? Thus, in a corner of the universe, the great silence birthed a question. It was perhaps the first time the cosmos had been asked to reflect on itself through the very beings made of its dust. In those early questions, uttered around flickering campfires or silently pondered under the wheeling stars, the universe itself found a voice. Through us, the cosmos began to speak and to ask. A strange paradox. Out of the universe's stillness grew minds that would not be still, that hungered to know. The night sky's grandeur made early humans feel both awe and mystery. They saw patterns in the stars and spun stories, sensing perhaps that the darkness was not empty, that there was something vast and eternal out there, beckoning. Who placed the stars in the sky? What lies beyond that glittering curtain? Is the universe around us all there is, or just a piece of something far greater? These questions, simple and profound, were the beginning of our journey. And they have no end. As though space itself were whispering to us, we felt an urge to explore, to seek the limits of what we can see. We learned to build tools, first telescopes of glass and metal, later great observatories, to extend our vision deeper into the silence. With each improvement of our cosmic eyes, the known universe grew. What once was a dome of twinkling lights became an ocean of stars, then countless galaxies, and then structures beyond galaxies. We discovered that the stars are not scattered randomly. They are gathered in immense cities of stars, the galaxies, each containing billions or trillions of suns. Our own Milky Way is one such city, a flat disk of light arcing across the sky. And beyond it, we found others. Andromeda, the whirlpool shapes of spirals, the blob-like ellipticals, the tiny dwarfs swarming around bigger ones. We realized the universe is composed of these galaxies scattered through space like handfuls of luminous sand tossed into the dark. Through patient observation, we determined the scale of our cosmic neighborhood. Light, that fastest of messengers, takes years to cross the gulfs between stars and millions of years to travel from one galaxy to another. We began to grasp that the lights in the sky were incredibly distant. The deepest images, taken with sensitive instruments, staring for days into what seemed like an empty patch of sky, revealed a staggering sight. Hundreds of galaxies in just a pinprick of darkness. It was like finding a shimmering city on what looked like a blank horizon. Everywhere we point our telescopes, if we look long enough, galaxies appear. The observable universe, the portion we can in principle see, contains at least 2 trillion galaxies, each with billions of stars. These numbers defy imagination. Even as we say them, do we truly understand? Each galaxy, an island of stars, perhaps with planets and wonders of its own, multiplied by trillions. The scale humbles us. We sit on a small planet orbiting one star among those countless, and we realize we are tiny. Our world is a mere grain of sand on an endless beach. As our knowledge expanded, so did our questions. We found that the universe has an edge, but not an edge in space like a wall or boundary we could touch. Rather, a limit in time and light. We call it the observable universe, the region from which light has had time to reach us since the universe began. There may be more beyond, much more, but it lies forever outside our view, hidden behind a horizon of light. Why can't we see beyond? Because the universe has a finite age. About 13.8 billion years since the Big Bang fireball ignited existence as we know it. Light from very distant regions simply hasn't had time to travel to us yet. Imagine being in a vast wilderness at night with a lantern. You see trees around you in the lantern's glow. Beyond a certain distance, the forest is dark, not because it ends there, but because the light hasn't reached those faraway trees. Our cosmic horizon is like that, a sphere of light around us, 46 billion light years in radius, beyond which the universe fades into an unknowable darkness. And yes, that horizon's radius is larger than 13.8 billion light years because space itself has been stretching all the while, carrying distant galaxies further out. We peer out to the edge of what we can see, and it appears like a foggy wall, not a solid barrier, but a limit of clarity. That fog is actually the afterglow of the Big Bang, the cosmic microwave background radiation, faint heat left from the time the universe was a hot, dense plasma. It's as far back as light can show us, a view of the universe when it was only about 380,000 years old, beyond which it was opaque. So here we stand, creatures of stardust and curiosity, staring at the cosmic horizon. We strain to see if beyond that faded glow of the primordial fireball, there might be more, perhaps endless galaxies receding into eternity. We suspect the universe doesn't simply end past what we can see. The evidence whispers that space likely continues far beyond our observational reach. The patterns of temperature in that cosmic afterglow are almost too smooth, too uniform, as if our observable patch is just a tiny piece of a much larger whole. If the cosmos ended just past our horizon, space would likely curve visibly or wrap strangely. Instead, all measurements indicate space is very nearly flat on the largest scales, with no detectable curvature as far as we can tell. This implies either the universe is infinite, stretching on without end, or so vast and curved so gently that we have not yet seen the bend. Most cosmologists lean toward the idea that it might be effectively infinite, or at least extremely large beyond comprehension. If that's true, our observable universe could be a mere grain in an infinite desert of universes. Think about that for a moment. Beyond the furthest galaxy we can see, there may be countless more galaxies, and beyond them more without edge. If space truly goes on forever, then somewhere out there, far beyond the reach of any telescope, other beings might gaze at their night sky and see a patch of galaxies that includes our Milky Way as just a faint smudge. Or perhaps they are so distant that even our whole observable universe is just a tiny part of their view. In an infinite cosmos, possibilities become certainties. Somewhere, the arrangements of matter must repeat. It boggles the mind, but in an infinite expanse, there could be another region so far away that it is identical to our own in content. Another patch of space with galaxies arranged just like ours. Another Earth with someone just like you, reading these very words. This isn't science fiction. It's a logical implication of infinity, although it's practically unobservable and forever beyond our interaction. The idea is dizzying and a bit unsettling. An infinity of other realities just out of reach. Yet it reminds us how limited our perspective is. We sit in our tiny bubble of space-time and see 93 billion light-years across. But that might be like looking through a keyhole and thinking that's the entire world. We simply don't know how far the grand stage extends. The true extent of the universe could be infinite, or the universe might eventually loop back on itself in a grand cosmic curve, like the surface of a sphere, but in 3 dimensions. If space is curved into a finite shape without a boundary, it's conceivable, though unlikely in light of current data, that if we traveled in one direction far enough, billions of light years, we might someday end up back where we started, coming up behind ourselves like a traveler circumnavigating a globe. Some scientists have even speculated about exotic shapes for space. One proposal imagined the universe's shape as a kind of dodecahedron, a 12-faced polyhedron, stitched together in a way that the cosmic microwave background might show repeating patterns. For a time, there were hints in the data, faint patterns that could suggest we were seeing the same regions of space in multiple directions, as if light had wrapped around the universe. But so far, these hints have not solidified into proof. The simplest explanation, flat and potentially infinite, remains most plausible. Yet the shape of the universe, its global geometry and topology, remains one of those great unanswered questions. Is the cosmos infinite or finite? Does it have an overall curvature or a unique topology beyond our horizon? We live suspended between possibilities, unable to step outside the universe to see it from the outside. Standing on the shores of the cosmic ocean, we realize that not only is there a limit to what we can see, but that the universe is astonishingly old and dynamic. The cosmos we observe is not eternal and unchanging. It has a history. The galaxies are flying apart, space itself stretching and carrying them away from each other. When we first discovered in the early 20th century that distant galaxies all seemed to be rushing away, it was as if the universe were breathing out, expanding. Rewinding this expansion with our calculations, we found it all converges back to that fiery beginning, the Big Bang. That was a revelation. Our universe had a birth in time. There was a moment, however brief, when all that we see, and all that we cannot see, was concentrated in an inconceivably hot, dense state. Before that, we do not know if before even exists in a meaningful sense, since time itself might have begun with the Big Bang. This origin story is derived from solid evidence: the expanding space, the cosmic background radiation, the mix of light elements. Yet it leaves us with profound mysteries. What ignited the Big Bang? What, if anything, came prior? Was it truly the beginning of everything, or just the beginning of our cycle of reality? We humans, naturally curious, push against the curtain of the unknown. We have conjectured many ideas for what set the stage for our universe. Some propose that our Big Bang might have been one of countless others, Perhaps the universe goes through cycles of birth, death, and rebirth, a bouncing cosmos that contracts and then explodes anew, over and over. Others imagine our universe budding off from a parent multiverse, a foam of bubble universes endlessly forming like bubbles in boiling water, each bubble a universe with possibly different properties. In such scenarios, the Big Bang was not the absolute beginning, but simply our bubble's local genesis. Still others invoke the idea of quantum fluctuations. Maybe nothingness is inherently unstable, and a tiny fluctuation could tunnel into creating an entire universe. Our cosmos could have sprung from a quantum event out of a vacuum of some higher reality. These ideas venture far beyond the realm of testable science, at least for now, but they arise naturally from our attempt to answer the question of origins. The truth is, we don't know what caused the Big Bang, or if that concept even makes sense in the absence of time. The very word cause assumes time already exists to allow an effect to follow. And if time began at the Big Bang, asking what came before might be as meaningless as asking what's north of the North Pole. Not knowing, however, does not stop the questions. It fertilizes them. Each mystery begets more wonder. We gaze at the observable universe, at that limit of perception, and wonder, if there are things forever beyond our sight, how can we ever know them? Perhaps we cannot, but we can infer hints. For example, our observable universe seems remarkably uniform in temperature in all directions. Even regions that are so far apart, light couldn't travel between them in the age of the universe to even out the heat. How did opposite ends of the sky agree on the same temperature without being in contact? To solve this puzzle, scientists proposed a radical idea: inflation. In the infant moments of the cosmos, a fraction of a second after the Big Bang, space itself might have blown up exponentially fast. An extreme expansion that took a tiny, uniform region and stretched it so vast that all we see now originated from that same patch. This would explain why distant parts of the sky have the same ancient heat signature. They were once close before inflation shoved them far apart. Inflation neatly accounts for some observed properties, suggesting our whole observable universe was once an infinitesimal speck. But inflation, if true, also dramatically broadens our perspective. That initial tiny region after inflation became huge, far larger than what we now observe, and inflation might not have been a one-time event that ended cleanly everywhere. Many inflation theories predict that inflation might be eternal, still occurring in far-flung regions, continually spawning new bubbles of space that themselves go on to expand and cool, becoming universes in their own right. In this picture, our universe is one bubble among a potentially infinite multiverse. Each bubble might have different physical conditions, different types of particles, even different dimensions or laws. We have no way, at present, to confirm the existence of other universes. They would be beyond our horizon, causally disconnected from us. Yet the theory that predicts them arose from trying to explain things we can see, lending some credence to the concept. The multiverse idea tickles the imagination. It suggests a reality far larger or more varied than anything we can directly detect. If true, the great silence beyond our cosmic horizon might be filled with other universes we will never know, a sobering and exhilarating possibility. Some of those universes could be barren, lifeless expanses where stars never formed. Others might be strange, with physics so alien that atoms as we know them can't exist. And perhaps some might be kindred to our own, with galaxies and stars, maybe even life. Of course, these speculations might forever remain philosophical musings. Without evidence, they remain in the realm of the unknown. But it is astonishing that human minds, products of a single universe, can even conceive of realities beyond it. Our imaginations press outward to the ultimate limits of existence, refusing to accept an end to the story. The cosmos, through us, is pondering what lies beyond itself. Yet, even as we dream of multiverses and infinite space, we must contend with enigmas right here in the observable universe, mysteries woven into the fabric of the cosmos we see. In the late 20th century, as our instruments grew more precise, we encountered one of the most profound. We realized that we understand only a tiny fraction of the cosmic contents. All the stars, planets, galaxies, everything that shines, or that we can detect with any form of electromagnetic radiation, amount to a mere 4 to 5% of the total mass energy of the universe. The rest, the vast majority, is invisible to our eyes and instruments, yet its presence can be felt through gravity. This realization dawned gradually, starting with the way galaxies rotate. We expected, based on the gravity of visible stars and gas, that stars at a galaxy's outskirts would orbit more slowly, just as planets farther from the sun move more slowly, weakened by distance. But to our surprise, we observed that stars in the outer reaches of galaxies were moving just as fast as those closer in. It was as though some extra gravitational force was present, something we couldn't see, holding the outer stars in orbit and preventing them from flinging away. The same unseen influence showed itself in other ways. Clusters of galaxies, huge collections where hundreds of galaxies orbit a common center, were behaving as if they had far more mass than what our telescopes could account for. Light from distant galaxies was found to be distorted and magnified by massive invisible clouds, like a giant lens made of something transparent. All these clues pointed to one conclusion. An unknown form of matter permeates the universe, outweighing normal matter by a factor of about 5. We called it dark matter, not because it's dark like soot, but because it neither emits nor absorbs light. It's utterly invisible, detectable only by its gravity. What is dark matter? We still don't know. It could be some new kind of elementary particle that doesn't interact with light or normal atomic matter except through gravity. Perhaps faint, ghostly particles left over from the Big Bang that pass through Earth and through our bodies by the billions every second without a trace. Experiments deep underground and in particle accelerators are attempting to catch a glimpse of a dark matter particle. But so far, they've only placed limits on what it could be. It's humbling. We have this elegant theory of fundamental particles and forces, the Standard Model, that describes atoms and light and so much else, and yet it doesn't include a particle that can account for dark matter. So either there is physics beyond our current theories, a new particle, a supersymmetric partner, a hidden sector of forces, or, just possibly, our understanding of gravity on large scales might be incomplete, meaning what we attribute to unseen matter could be a subtle shift in how gravity works over vast distances. Most evidence favors actual dark matter substance, because the patterns are hard to explain with modifications of gravity alone. Dark matter is like a shadow universe overlain on the one we see. It formed a cosmic scaffolding in the early universe. Imagine an invisible web, filaments and knots of dark matter, and normal matter fell into its gravitational wells. This process seeded the formation of galaxies and clusters along the dark matter web. In a sense, the luminous structures we observe, galaxies, stars, planets, and us, are arranged on the template that dark matter provided. Yet we cannot directly behold this scaffolding. We map it indirectly by observing how it bends light, gravitational lensing, and how it influences the motions of galaxies. What an irony that most of the universe's mass is invisible to us. We are like fish swimming in water, yet not seeing the water, only sensing its currents. The dark matter neither shines nor bumps into atoms in a way we can easily measure. It whispers to us only through gravity, the subtlest of clues. We have given it a name. We hunt for it with detectors in deep mines and in the Large Hadron Collider. And perhaps one day we'll finally hear its voice. Until then, it remains a tantalizing mystery, a vast, unknown sea in which the islands of stars float. As if that weren't enough, an even stranger revelation awaited us. At the turn of the 21st century, astronomers painstakingly measuring the expansion rate of the universe made a shocking discovery. They expected to find that the expansion, slowed by gravity over time, was either coasting gently or perhaps starting to decelerate more strongly if the universe had a lot of matter. Instead, they found that the expansion isn't slowing at all. It's speeding up. The galaxies are not just rushing apart, they're accelerating away from each other, like a driver who, instead of coasting uphill, suddenly floors the gas pedal. This was the last thing anyone expected. Whatever could be causing this acceleration was not something we could see. It wasn't normal mass, which would attract, not repel. We named this mysterious phenomenon dark energy, a term that is a placeholder for our ignorance. Dark energy seems to make up about 70% of the total energy content of the cosmos, dwarfing even dark matter, which is 25%, leaving ordinary matter as a cosmic afterthought. What is dark energy? That question cuts to the core of our understanding of physics. One possibility is that dark energy is a property of space itself. In the equations of general relativity, Einstein's theory of gravity that describes how matter and energy tell space-time how to curve, there is a term, the cosmological constant, which Einstein once introduced and later retracted, thinking it unnecessary. This term corresponds to an inherent energy of empty space, an energy that doesn't dilute as space expands. If space has an innate energy, it would act like a sort of pressure or anti-gravity that pushes things apart. And indeed, this cosmological constant idea fits the observations fairly well, a constant energy density in space that started dominating the universe's dynamics a few billion years ago, causing expansion to accelerate. But why would such a constant exist? And why of that particular magnitude? When physicists try to calculate how much energy empty space should have, based on quantum theory, where even vacuum teams with virtual particles popping in and out, the theoretical value comes out enormously larger, a ghastly mismatch with what we observe. It's one of the worst disagreements between theory and observation ever encountered, signifying we deeply misunderstand something. So perhaps dark energy isn't a simple constant. Maybe it evolves, a dynamic field that changes over time, a concept dubbed quintessence after the fifth element of the ancients. Quintessence would be a new substance or field filling space, one that can vary from place to place or era to era, and whose properties we have yet to determine. Another wild possibility, perhaps our understanding of gravity needs revision at the very largest scales. Maybe, like Newton's laws were superseded by Einstein's relativity might itself be a limiting case of a deeper theory that yields an accelerating cosmos without invoking a mysterious energy. For now, dark energy remains an enigma. It's as if we're children who notice that a top is spinning faster on the tabletop than it should, yet we can't see the hand twisting it. The universe's acceleration is a clue that our cosmic story has a twist, literally a speeding up, and we're in the dark, pun intended, about why. What we do know is that given this acceleration, the future is quite bleak for our view of the cosmos. If dark energy continues to push the expansion, distant galaxies will rush away faster and faster. Far in the future, beyond tens or hundreds of billions of years, other galaxies might recede so far and so fast that their light can no longer reach us. An observer in that far future might see an empty universe, just their own galaxy and nothing else, unaware that other galaxies ever existed. The thought that the rich cosmos we observe is a temporary gift of this epoch is poignant. We happen to live when the universe is young enough that galaxies are still in view. The accelerating expansion means the vast majority of galaxies are slipping beyond reach, like ships sailing over a horizon from which they'll never return. But why this is happening? Why now, and what exactly dark energy is? Those answers elude us. The silence regarding dark energy is profound. We can measure its effects with exquisite precision, yet the cause of those effects remains a whisper from the void. From the grandest scales of the expanding universe, let us turn inward to one of the most fearsome and fascinating objects nature allows: black holes. These are regions where matter has been crushed into such density that the fabric of space-time itself has curled in on itself, creating a pit from which nothing, not even light, can escape. A black hole forms, for example, when a massive star reaches the end of its life. The star's core collapses under its own weight, compressing beyond even atomic structure, beyond anything we can properly imagine, until it becomes an infinitely dense point, a singularity, wrapped in a spherical cloak of gravity. The boundary of that cloak is called the event horizon. Once you cross that threshold, there is no return. The concept of an event horizon is chilling and intriguing, a one-way membrane in the universe. Outside it, space and time behave normally. Inside, all paths inexorably lead down to the central singularity. It's a point of no return, a cosmic trapdoor. Black holes challenge our understanding of physics at a fundamental level. According to general relativity, the singularity at the center has infinite density and zero volume, a place where the known laws of physics break down completely. This signals that our theories are incomplete. Infinities in equations often mean we're pushing the theory beyond its domain of validity. We need a theory of quantum gravity, combining quantum mechanics with gravity, to fully describe what happens at those extreme densities. But we don't yet have that theory. So inside the black hole, hidden from our view by the horizon, nature keeps her deepest secret. It's as if the universe has places it refuses to show us, where it hides the answers to the final exam of physics. What would it be like to fall into a black hole? Imagine approaching a black hole in a spaceship. From a safe distance, it might actually be quite invisible unless it's feeding on surrounding matter, which can glow brilliantly as it heats up falling in. If it's a solitary black hole, you'd see stars behind it, warped into rings or arcs by its intense gravity, gravitational lensing. As you got closer, the pull on your ship would increase. If the black hole is of stellar mass, the gradient of gravity between your nose and tail is so steep, it would stretch you out in a process morbidly named spaghettification. You'd be torn apart before you even reached the horizon. But if it's a supermassive black hole, like the ones at galactic centers, millions of times the mass of the Sun, the tidal forces at the horizon might be mild, since the gravity, while strong, changes more gradually across your body. In that case, you could actually cross the event horizon without immediate destruction, and perhaps without even noticing crossing it, since nothing particularly physical marks that boundary aside from the point of no return property. Once inside, however, all paths lead to the center. Your engines, no matter how powerful, cannot reverse course. Time and space trade roles in a sense. Just as you cannot stop moving forward in time, now you cannot stop moving toward the singularity. According to classical relativity, within a short time, you reach the central singularity and are crushed. Your mass adds to the black hole, your identity lost. But physical intuition rebels. Is information truly destroyed in a black hole? Quantum theory says information about a system's state cannot be lost. At least, that's a principle of quantum mechanics as we understand it. If a black hole simply eats things and then evaporates, we suspect black holes slowly evaporate via Hawking radiation, a faint glow due to quantum effects at the horizon. What happens to the information that fell in? Hawking radiation, as originally conceived, carries no information. It's like heat radiating from a warm object, basically random. If a black hole completely evaporates away, does the information of everything it consumed just vanish from existence? That possibility horrified physicists, as it seemed to violate a sacred tenet of physics: information conservation. This is the famous black hole information paradox. Some think the information is encoded in subtle correlations in the Hawking radiation, so that in principle, if you capture all the radiation, you could reconstruct what fell in. Others have proposed exotic solutions. Perhaps the singularity isn't the ultimate end. Maybe it somehow connects to a new region of space-time, a budding universe or a white hole, theoretical time-reversed black hole that spits matter out. Some suggest that what we call singularity might be a mischaracterization, and quantum gravity, when understood, will show no infinite crunch, but something like a bounce or a portal. Yet others imagine that black holes might have firewalls at the horizon, blistering zones of quantum energy that destroy information before it even reaches the singularity, thus preserving quantum rules, but at the cost of violating Einstein's predictions of a smooth passage through the horizon. We just don't know the answer yet. Astonishingly, what was once theoretical musing, we have now seen. In recent years, humanity managed to capture an image, via radio telescopes arrayed across Earth, of a black hole's shadow, essentially the silhouette of the event horizon against the backdrop of hot plasma around it. The first such image, of the supermassive black hole in the galaxy M87, showed a fuzzy donut of light, just as predicted by general relativity. We have also measured gravitational waves, ripples in space-time itself, from black holes colliding, hearing the literal ringing of space-time as they merge. These observations confirm that black holes are real, not just mathematical quirks. They exist in the universe by the dozens, likely by the millions. Our own Milky Way harbors a giant black hole at its core, over 4 million times the mass of the Sun. Stars orbit this invisible monster like comets around a phantom sun. And nearly every galaxy likely has one, with masses from millions to billions of solar masses, shaping the evolution of their host galaxies in ways we're still investigating. So black holes stand as both a triumph of understanding — we predicted them, then observed them — and a frontier of mystery. Their insides remain terra incognita. They force the question of how the very large, gravity and space-time, and the very small, quantum particles, mesh together. To truly know what a singularity is, or what happens at that boundary of physics, we will need a unified theory that marries quantum mechanics with general relativity. It's often said that at a black hole's center, the equations of general relativity yield infinity, meaning the theory throws up its hands. It's as if at that point, the universe is saying, "Here, your current understanding halts. A new understanding must begin." In the same vein, consider the nature of time itself, another profound mystery at the intersection of physics and philosophy. Time is something we all experience intimately, yet when we scrutinize it, it becomes elusive. We feel time flow. Every moment, we sense the now moving inexorably to the next now. We remember a fixed past. We anticipate an unknown future, and we seem trapped in this ever-moving present. But what is time? Physics treats time as a dimension much like space. In relativity, time and space are intertwined as space-time. Just as we can move north-south or east-west, we also move forward in time. But why do we only move in one direction in time, whereas in space, we can turn around? Why is yesterday set in stone and tomorrow so contingent? This one-wayness is called the arrow of time, and it appears most strongly when we consider entropy, the measure of disorder. The second law of thermodynamics says entropy in an isolated system tends to increase. Eggs scramble, but they don't spontaneously unscramble. Smoke disperses from a fire, but never gathers itself back into logs. In short, things tend to move from order to disorder, from concentrated energy to spread out energy. This provides a kind of arrow from a past of lower entropy to a future of higher entropy. Our memories and records are traces of lower entropy states. Perhaps the reason we remember the past and not the future is simply that the past is embedded in those ordered traces, like photographs, fossils, neurons in our brain, whereas the future hasn't left any traces yet. In this view, the arrow of time is a brute fact about initial conditions. The universe started in a very low entropy, highly ordered state. The Big Bang, despite being hot and dense, was actually very uniform, which is a kind of order. As the universe evolves, entropy increases. Stars burn fuel and produce heat, matter clumps and then energy dissipates, etc., thus giving time a direction. But this explanation, while broadly accepted, just pushes the mystery back one step. Why was the entropy low to begin with? Why was the early universe so orderly, laying the groundwork for an arrow of time that would later allow life and memory? We don't know. It might be a fortunate accident, or it might hint at deeper cosmological structure. For instance, in some multiverse scenarios, maybe new universes always start fresh with low entropy as they pinch off, and we naturally find ourselves in one of those. Another puzzle. At the microscopic level, the fundamental laws of physics, ignoring a subtle detail with certain particle decays, are mostly time-symmetric. They don't care if time runs forward or backward. If you filmed two particles scattering off each other and ran the movie backwards, you'd see a perfectly valid physical process. Yet at the human scale, time's asymmetry is obvious. How do those reconcile? The prevailing view is that the asymmetry isn't in the underlying laws, but in the boundary conditions. Again, that low entropy past. Thus, the flow of time might be emergent, not fundamental. Some scientists even propose that time as we perceive it, a flowing river, is an illusion, a byproduct of our consciousness stringing together events, whereas in reality, all moments might coexist in a block universe. In that block universe picture, the past, present, and future are all equally real, just different coordinates in space-time. And it's only our particular perspective, like a spotlight moving along the timeline, that gives a sense of flow. This interpretation is mind-bending because it means now is not a universal truth, but a subjective one linked to each observer. Relativity already showed that simultaneity is relative. Two events that are simultaneous for you might not be for me if we're moving differently. So in a deep sense, the notion of a global present is tricky. Is time perhaps an emergent phenomenon from something deeper, like entanglement or quantum states? Some cutting-edge ideas suggest time might arise from quantum entanglement patterns, or that our universe's time dimension could have sprung forth from a timeless quantum reality when certain conditions were met. These remain speculative, but they remind us that something as fundamental as time is still not fully understood. Time is at once the most familiar thing and the greatest mystery. We live in time. We cannot step outside it to examine it objectively. That's akin to asking a fish to describe water. It's so ubiquitous that it becomes elusive. We mark time's passage with clocks and calendars, but what we're really measuring is change relative to other change. A second is defined in physics by a certain number of oscillations of a cesium atom's radiation, for example. So time is tied to processes. If nothing changed, would time have meaning? In the vast stillness before the universe, if such a state can even be contemplated, what was time? Or did time begin when change began? The silence of the cosmos extends into the subatomic world as well, where our everyday intuitions falter. Peering into the quantum realm, we found uncertainty and paradox. The building blocks of reality, electrons, photons, and other quantum particles, do not behave like little billiard balls following neat paths. Instead, they exist as fuzzy clouds of possibility, described by a wave function that tells us only the probability of finding them in a particular state. It's as if, at a fundamental level, nature doesn't decide on an outcome until something forces its hand, namely, an observation or interaction that makes the potential become specific. This is encapsulated in Heisenberg's uncertainty principle. One cannot precisely know certain pairs of properties, like position and momentum, at the same time. If you pinpoint a particle's location, its momentum becomes uncertain. If you know its momentum exactly, its location smears out. Nature, it seems, imposes a fundamental limit on how much we can know, or perhaps on how much is decided, even in principle. This isn't a limit of technology, but of principle. It's as though the universe, at fine scales, refuses to give a straight answer, offering instead a spread of possibilities. Consider the famous double-slit experiment. When we send electrons or photons one by one through two narrow slits to a screen, an interference pattern emerges, as if each electron were a wave that went through both slits and interfered with itself. Yet, when we put detectors to see which slit the electron actually went through, the interference disappears. The electron acts like a particle that went through one slit or the other, not both. It's as if the electron exists in a ghostly blend of possibilities, both paths, until we look, and then it chooses one path, retroactively making itself a particle that had gone that way all along. This kind of behavior defies our classical logic, and the universe stays mum on how or why it happens. Various interpretations of quantum mechanics try to make sense of it. Some say the wave function collapse is just fundamental and random. Others propose that each possible outcome actually branches off into a separate reality, the many worlds interpretation, where the electron went through left slit in one branch and right slit in another, and these two branches do not interfere once decoherence, entanglement with environment, has happened. Many worlds offers a wild vision. Every quantum event spawns a new universe, so there is an ever-branching multiverse of possibilities. If true, then at this very moment, innumerable versions of reality are splitting off for every quantum choice. In some, you took a breath a second later than in others. In some, a butterfly flapped its wings, whereas in others, it stayed still, and those small differences proliferate. This would be a multiverse of a different kind, not separated by vast distances, but coexisting on top of each other in a higher dimensional quantum space, splitting at each interaction. It's a solution to making quantum mechanics purely deterministic. No randomness, just every outcome happens in some branch. But it means that reality is unimaginably more complex than we perceive. Yet from within one branch, we can never communicate with the others. So how could we ever tell if this is true? The cosmos yields phenomena that invite such bizarre explanations, and then remains silent, leaving us to debate and wonder. Another perplexing quantum phenomenon is entanglement, what Einstein famously called spooky action at a distance. When two particles are entangled, they share a single quantum state. If you separate them across the galaxy and then measure one, instantly the other is affected, or rather, instantly you discover that the outcome on one side is perfectly correlated with the outcome on the other side, as if they were connected. For example, two photons can be entangled in polarization, such that if one is measured to be vertically polarized, the other will always be found horizontally polarized, say the opposite, no matter the distance. It's not that one sends a signal to the other at measurement. As far as we can tell, nothing travels between them, and indeed, if you try to use this for communication, it fails. You can't actually send a message this way. Instead, it's as if the two particles are a single entity described by one combined wave function, and when you collapse it by measuring one, you simultaneously collapse the whole system. This is deeply counterintuitive. It implies the universe has non-local qualities. Parts of the universe far apart can be intimately linked in ways that transcend ordinary space and time relationships. Experiments have confirmed entanglement again and again. It's real. We even have technologies exploiting it, quantum cryptography, for instance. But why the universe allows this deep connectedness, how it fits with our concept of locality, and what it means about the underlying reality, remains mysterious. Some thinkers speculate that perhaps space and time themselves are not fundamental, and entanglement hints at a more basic fabric of reality from which space emerges. Picture that what's fundamental is information or relationships, and what we perceive as space is just a way of organizing those relationships for our macro understanding. In such a view, two entangled particles might be adjacent in the deeper reality, even though in our three-dimensional space they are far apart. Thus their coordination is instantaneous because distance is irrelevant in the underlying layer. This is speculative, but it's an attempt to make sense of what nature is quietly demonstrating to us without explanation. The silence of the quantum world, the lack of an intuitive story from nature about what's really happening, has haunted physicists and philosophers for a century. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." It's a humbling admission that even our best theory confirmed by experiment to astonishing precision, is something we can use, mathematically, but not fully comprehend in plain language. Is the electron a particle or a wave? The only honest answer, it's something quantum, which has aspects of both, and depending on how we interact with it, it will manifest one aspect or another. It's as if reality at base is described not by the solid objects of our sensory experience, but by ghostly probability clouds and interconnections that defy straightforward description. We've developed a comfortable routine with quantum mechanics. Shut up and calculate, some say. Yet the human spirit itches to truly know, to have a picture, a narrative, something that feels resolved. And so far, the cosmos offers none. Perhaps one day a deeper theory, like a successful quantum gravity theory or a theory of everything, will unify these pictures and give us a new paradigm that makes quantum weirdness feel as natural as sunrise. Until then, we live with a fundamental not knowing at the heart of physics. Our journey through the unknown wouldn't be complete without reflecting on the mysteries that hit closest to home. We've looked outward to the edge of the universe and inward to subatomic realms. But what about life? What about consciousness? These are aspects of the cosmos too. After all, we are part of the universe, made of the same particles and subject to the same laws. In the cosmic perspective, life is a recent phenomenon, blossoming on at least one small world. But is it unique to Earth or common as starlight? This is one of humanity's oldest questions. Are we alone? The Earth teems with life in astonishing variety and tenacity. We find life flourishing in boiling hot vents at the ocean floor, in acidic lakes, in the frozen Antarctic permafrost, and high in the atmosphere. Life, once it gains a foothold, is hardy and adaptive. This gives us hope that life could exist beyond Earth, in niches we once thought too extreme, perhaps in the subsurface oceans of icy moons like Europa, or Enceladus, or in the cloud decks of Venus, or on planets orbiting distant stars. We have now discovered thousands of exoplanets, planets around other suns. Some of these are in the so-called habitable zone, where temperatures might allow liquid water. A few are near Earth size and could be rocky. The sheer number of planets in our galaxy is staggering, likely on the order of 100 billion, roughly one per star on average, and many stars have multiple planets. With billions of galaxies, the number of planets in the observable universe might be more than all the grains of sand on all Earth's beaches. If even a small fraction of those planets are habitable, the number of living worlds could be enormous. And yet, we have not heard a peep. The universe, as far as our searches have detected, is quiet about life beyond Earth. No radio signals from alien civilizations beam through the sky, despite our listening via SETI for decades. No unmistakable technological signatures or visits, despite UFO lore. There's no confirmed evidence of extraterrestrial craft. We see no obvious ruins on Mars or elsewhere in the solar system. This great silence is puzzling. It's termed the Fermi paradox. Given the vastness of the cosmos, and presumably many opportunities for life, why have we not encountered anyone or anything? Where is everybody? Enrico Fermi famously asked. There are many possible answers, none confirmed. Maybe life is common, but intelligent life is exceedingly rare. Perhaps simple microbes abound on many worlds, in the oceans under ice crusts of moons, or beneath the soils of exoplanets. But the evolution of complex multicellular life, and then technological intelligence, is an extremely improbable chain of events. After all, for most of Earth's history, billions of years, life remained single-celled. Only in the last 500 million years did complex organisms proliferate, and only in the last few million did a species arise with intelligence capable of radio telescopes and rockets. Perhaps in many biospheres that step never occurs. Life stays microbial or animalistic, never building cities or machines. Or maybe civilizations do emerge on many planets, but they tend to have short lifespans. They might self-destruct via warfare or environmental collapse. Or perhaps they inevitably transition to some other state, like a virtual reality existence, and lose interest in communicating with the stars. It could even be that a galaxy teems with life and intelligence, But it's largely quiet and inward-looking, and the distances are so vast that communication is difficult. Signals might be rare, or we might not recognize them. Perhaps advanced beings use communication methods we haven't discovered, or maybe they abide by a cosmic etiquette, a prime directive, of not interfering with emerging civilizations like ours. It's also possible we are alone, or at least incredibly rare. Maybe life itself is a freak occurrence, needing such a special convergence of circumstances that Earth might be one of only a handful of places in the whole galaxy or beyond where it happened. Some scientists have suggested that certain unlikely events, like the origin of life from chemistry, or the jump from single cells to complex organisms, or the development of intelligence, might be low-probability flukes. If so, the universe could be mostly sterile, with us as a precious exception, or one of very few. That thought is both exhilarating, we're special, and terrifying, so fragile in the cosmic darkness. If we are rare or alone, it puts a huge responsibility on us to survive, to cherish life, to perhaps spread it. We are searching avidly for answers. Our robots crawl on Mars, drilling into rocks to find traces of past microbes. Our probes have sampled the plumes of Enceladus, shooting water from its subsurface ocean into space, and found organic molecules, tantalizing, though not proof of biology. We're designing missions to Europa and other worlds. And from Earth, or Earth orbit, we are beginning to peek at exoplanet atmospheres. We've detected atmospheres on a few distant planets, and soon next-generation telescopes will try to find signatures of life. For example, an atmosphere rich in oxygen, which on Earth is maintained by life, or weird combinations of gases that scream metabolism at work. It's a challenging task. Exoplanets are tiny and drowned out by their bright stars. But the endeavor is underway. Perhaps in the coming decades or centuries, we'll get our first hint that biology is not unique to Earth. Imagine the day we detect, say, methane and oxygen and water vapor on an Earth-sized planet around a distant star, a combination hard to sustain without life. We will not hear aliens say hello, but we might finally know that the cosmic loneliness is an illusion, that life has filled other ponds in the great rain of creation. Until then, we have only questions and the emptiness between the stars. We've sent out our own signals, radio waves that have leaked from our transmitters for a century, spreading out as a faint bubble, 100 light years in radius, and we've deliberately beamed a few focused messages or carried plaques and golden records on spacecraft like the Voyagers. Those artifacts drift now in the interstellar void, likely to wander for millions of years. Perhaps one day, far future, some alien hand, or appendage or machine, will find our little bottles in the cosmic ocean and know that we existed. But for now, the only confirmed life in the universe that we know of is here, on this pale blue dot. That is a sobering truth. It means every living thing we have ever known, every experience of love, joy, struggle, discovery, all of it, has occurred in a thin film of life on one planet's surface. Life is a delicate chemical flame fighting entropy, and Earth is the oasis that nurtures it in our solar system. This knowledge urges us to protect our world, for if life is rare, losing Earth's biosphere would be an unspeakable tragedy. And if life is common, well, then we have friends yet to meet, and we should keep our planet thriving so that one day we might join a galactic community. Either way, the quest to know if we are alone goes on, intertwined with our own future. And then there is consciousness, the most immediate reality to each of us. For what could be more certain than our own awareness? Yet perhaps the hardest phenomenon to explain in scientific terms. Somehow, in the 13.8 billion year journey from the Big Bang's fire to now, the universe has developed the ability to contemplate itself. Hydrogen atoms coalesced into stars. Stars forged heavier elements. Those elements made planets. On one planet, chemistry, begat life. Life grew brains, and now those brains contain minds that experience, question, and create. It sounds like a fairy tale, inert matter becoming sentient, yet it happened. In us, and likely in other creatures too, to varying degrees. Surely many animals are conscious in their own ways, though we humans possess a self-reflective awareness and intellect that sets us somewhat apart. How does mere matter give rise to the feeling of being? How does a collection of neurons, exchanging electrochemical signals, produce the redness of a rose, the taste of chocolate, the pang of sadness, the sense of self? This is often called the hard problem of consciousness, because explaining how the brain processes information, responds to stimuli, or controls the body, the easy problems. Those are difficult, but we can see how to approach them scientifically. But explaining why those processes should be accompanied by an inner subjective experience, why there is something it is like to be you from the inside, that's a different matter. We might map every neuron in your brain and track every spike and chemical, and still be left wondering at what point those physical events create a conscious experience. If a computer simulated your brain perfectly, would that simulation be conscious? Or is there something more than computation needed? Science, by design, deals with third-person observations, measurements of things from the outside. Consciousness is inherently first-person. It's the one thing you can't directly observe about me, nor I about you. I can tell you I feel pain or joy, and you can correlate it with brain activity or behavior, but the feeling itself is private. This gap between objective and subjective has led to philosophical standoffs for centuries. Mind-body problem, dualism versus physicalism, etc. The prevalent scientific view is that consciousness arises from brain activity, that the brain is the generator, or at least the transmitter, of the mind. If so, then consciousness should be explainable in terms of neurons and their interactions, but we haven't cracked how. There are intriguing leads. Certain brain processes correlate strongly with conscious states, for instance, synchronized oscillations in certain frequencies, or specific circuit loops in the cortex and thalamus. The Integrated Information Theory, IIT, suggests that consciousness corresponds to the amount of integrated information a system possesses, a measure noted as FEF. Under IIT, even a simple system might have a tiny bit of consciousness if it has a feedback structure that integrates information. So even a thermostat might have a minuscule glimmer of experience, which is a panpsychist kind of implication. Another theory, Global Workspace Theory, GWT, posits that consciousness is like a global blackboard in the brain, where information gets broadcast to many subsystems. What we experience consciously is the stuff that made it into this global workspace. These theories provide models and prediction, but none yet explains why the global workspace feels like something, or why integrated information should result in an inner life. Some thinkers have ventured that consciousness might be a fundamental property of the universe, like mass or charge, an idea known as panpsychism, the notion that perhaps all matter has some degree of consciousness, and complex systems like brains just amplify or collect it into the vivid awareness we know. This is not a mainstream scientific view, but it arises from the difficulty of explaining consciousness purely as emerging from non-conscious parts. If electrons and neurons are totally devoid of experience, how do a trillion of them together produce experience? Panpsychism answers, maybe electrons, and all particles, have extremely rudimentary proto-consciousness, some intrinsic aspect that is mental, and when arranged in complex ways, these form higher consciousness. It's a wild idea, harking back to ancient philosophies that saw spirit in all things. Whether true or not, it underlines how desperate the attempt to solve consciousness has become, that even such ideas get consideration. Alternatively, maybe consciousness is an emergent phenomenon that will eventually be explained in terms of information processing, but we just haven't found the right concepts yet. After all, concepts like temperature and pressure were once mysterious. How does the jostling of atoms create the feeling of warmth? But kinetic theory explained them. Perhaps one day we'll likewise demystify conscious experience, showing how certain patterns of computation just are the subjective feeling from the inside, similar to how a certain frequency of air vibrations just is the subjective experience of a musical note to an ear and brain. Some neuroscientists suggest that if you had a matrix of interconnected neurons or artificial units replicating the brain's structure, an inner life might spontaneously light up. But verifying that will be tricky, again, because we can't directly measure the consciousness, only infer it from behavior or reported experiences. For now, consciousness stands as an open question that straddles science, philosophy, and even spirituality. The cosmos has produced self-aware beings. We know this because we are them. But we don't understand the spark that lights up our thoughts. We don't know at what point in evolution consciousness arose. Do fish feel? Do insects? What about single-celled organisms responding to stimuli? Is there a faint glimmer of something it is like to be an amoeba? Does consciousness require a brain, or could an alien form of life, like a network of fungi or even a sufficiently complex machine, be conscious? Could the universe itself be conscious in some way, as some mystics and even a few scientists muse? Not in a simplistic anthropomorphic way, but in a sense that there is a level of awareness associated with the cosmos as a whole, or with fundamental fields. These questions drift at the edges of empiricism. They may not all be answerable, at least not by traditional experiments, yet they matter to us, because consciousness is the lens through which we experience everything else. Without it, we aren't even there to ask the questions. Let us step back now and look at the tapestry of what we know and what we don't know. The cosmos began, as far as we can tell, in silence and mystery, and that mystery remains at every level we probe. We have learned so much: the age of the universe, the recipe of elements, the existence of cells and DNA, the laws of gravity and electromagnetism, the reality of quantum fields, the genealogy of stars and galaxies, the expansion of space, the evolution of life. Our knowledge has blossomed, an impressive collective achievement for a species of former cave dwellers. And yet, what we don't know overshadows the patch of light we've kindled. The volume of ignorance is an ocean around our island of understanding. It humbles us, but it also excites and motivates us. Each generation has pushed further into that ocean. We often find that answering one question opens several new ones. We learned how stars shine, but that led to questions about stellar evolution and supernova. We discovered other galaxies, but that raised questions about dark matter to explain their motions. We uncovered the expanding universe, which posed the question of what the fate of expansion is and introduced dark energy. We deciphered the code of life, DNA, but then faced the complexity of how genes lead to consciousness. It's like climbing a mountain. Each time you reach a summit, you find a higher peak beyond. Far from being disheartening, this is invigorating. It means the adventure continues, perhaps forever. Consider the nature of space itself. At first glance, space seems like nothing, an empty void, the backdrop for matter. But we've come to see space as something with structure and activity. Einstein's relativity showed that space and time can stretch, bend, and ripple. Gravity, in that theory, isn't a force emanating through space. It is the shape of space and time itself, curved by mass and energy. When you put a heavy object like the sun in space, it dimples the space-time fabric around it, and the Earth orbiting the sun is like a ball rolling around a dent, following curves in space-time. This was a radical shift. Space is not just an inert stage, it's a dynamic actor. Then quantum physics adds another layer. Even a perfect vacuum, completely devoid of particles, isn't truly empty. It seethes with ephemeral phenomena, quantum foam, as some call it. Particles and antiparticles can briefly appear and annihilate. Fields fluctuate constantly at microscopic scales. There is a constant jitter in the vacuum, so much so that the vacuum, paradoxically, contains immense energy if summed, though our inability to tap or see most of that energy is another puzzle. These vacuum fluctuations have real effects. They cause tiny, measurable forces. The Casimir effect, where two close plates have a slight attraction due to altered vacuum modes between them, and contribute to phenomena like the Lamb shift in atomic physics. So the nothingness of space is actually a roiling, boiling brew of potential, the foundation upon which everything rests. Space itself might undergo phase transitions. Some cosmologists speculate that in the very early universe, space was in a different state, with different symmetry between forces, and as it cooled, it crystallized into the form we know, possibly releasing energy that drove inflation. The vacuum today might hide exotic fields, like the Higgs field, which pervades space and gives particles mass, discovered experimentally in 2012. A tangible example that space contains fields with constant values. Dark energy could be the energy of space's vacuum. If space has energy, then a volume of vacuum isn't truly nothing. It's more like a latent something. We're reminded of a line from a poet or sage that silence is not empty, it's full of answers. Similarly, space is not empty. It's full of the answers to questions we've yet to formulate. Yet for all that, when you stand outside on a clear night and look up, space feels like an immense, silent void between the stars. That serene emptiness cradles all of creation. It separates and connects everything. Every breath you take, the molecules were at one time scattered in space before the Earth formed. And after you exhale, given enough time, they may escape Earth and wander the galaxy. Space allows that movement. Space, by its vastness, also ensures that objects can exist without immediately colliding with one another. It grants stability to solar systems and galaxies by giving them room. But is space infinite? Does it go on forever? We addressed that earlier. We're not sure. If it is finite, what lies beyond? Perhaps nothing we can comprehend. Or perhaps our three-dimensional space is embedded in a higher dimensional reality. String theory suggests extra spatial dimensions we don't perceive, perhaps curled up small. Could it be that our space is like the surface of a balloon, and there is a higher dimensional space outside it? If so, that's outside our experience, and possibly forever inaccessible. Or maybe beyond all galaxies, beyond the cosmic horizon, space just continues, with more galaxies ad infinitum. So even space, the very fabric we exist in, holds mysteries. Some researchers think space and time might be emergent from something more fundamental, like quantum entanglement patterns or spin networks in theories of quantum gravity. Imagine if space-time is not the base level of reality, but a kind of approximate large-scale picture that arises from microscopic physics that isn't in space-time at all. This is speculative, but we already have hints that space and time break down at extremely small scales. The Planck scale, around 10 or 35 meters. At that scale, quantum foam might be so wild that the notion of a smooth space-time becomes meaningless. Space might be chunky or erratic, full of baby black holes popping in and out, wormhole connections blinking open and shut, a true quantum chaos. We have no microscope to see that deep. It's far beyond our current or foreseeable technology to probe distances that small directly. But mathematical attempts at quantum gravity, like loop quantum gravity or aspects of string theory, suggest space-time could have an atomic or quantum structure. If so, then asking about the continuity of space or the absolute beginning of time might be like asking where exactly a flowing river ends when it fans into a delta. Up close, the distinctions blur. We cannot now answer if time had a beginning, or if space has an edge, or what space is made of, if anything. But we can marvel at the fact that we, ephemeral beings made of cosmic bits, can even frame such questions. Think of the journey, from silent stillness to swirling galaxies, to starshine on primordial Earth.
to life evolving in the oceans, to human minds reaching out with curiosity. We are a way for the universe to know itself. That poetic insight appears literally true. Our senses, our instruments, extend the universe's ability to perceive. Without conscious observers, would the majesty of the cosmos have any meaning? The galaxies would still dance, the stars would still burn, but there would be no appreciation, no insight, no knowledge. Through us, and maybe through other conscious creatures out there, if they exist, the universe gains the gift of self-awareness. We are the cosmos made conscious, and so we are a small part of the cosmos, looking back at itself and trying to understand. It's as if the universe has sprinkled seeds of awareness within itself, and those seeds, in the form of beings like us, awaken and stare out in wonder, asking questions. We ask about the Big Bang and black holes and quantum foam, but in a sense, the universe is asking those questions through us. Space itself speaks in our questions. The great silence of outer space finds a voice when a scientist in a lab theorizes or an artist at night paints the Milky Way. We feel the mystery, and we respond with curiosity. A fundamentally human trait, perhaps a fundamental cosmic trait expressed through humanity. Where do we go from here? The unknowns beckon us forward. We will keep building better eyes, telescopes to hunt for exoplanet atmospheres, to watch the birth of stars, to glimpse the first galaxies forming not long after the Big Bang. We will keep listening for signs of life or intelligence beyond Earth, refining our methods, maybe sending new messages or probes to nearby stars. We'll continue to smash particles together or devise clever detectors deep underground, hoping to catch whispers of dark matter or new physics. We'll push quantum theory to its limits, perhaps eventually developing quantum computers that might simulate aspects of reality we couldn't before, giving insight into those mysteries. Perhaps one day we'll integrate gravity and quantum mechanics into a single, coherent theory, a momentous achievement that could answer some of those questions, maybe revealing what really happens at a singularity or exactly how space-time emerges. And as we do, new questions will arise. Perhaps solving dark matter and dark energy will lead us to other puzzling phenomena. Perhaps understanding consciousness will open entire new realms of science about subjective experience. There's also a chance that some mysteries remain mysteries, either because they are fundamentally beyond our cognitive reach, or because obtaining the evidence is practically impossible, like a multiverse beyond contact, or what before the Big Bang was, if that concept even applies. But even then, exploring these ideas can enrich us. They make us grapple with the limits of knowledge, with the meaning of reality. Throughout all this, one truth remains. To not know is not a failing, but a feature of our existence. If we knew everything, the universe would lose its allure, its dynamism. Each of us in life starts not knowing, then learns, and in learning, discovers more things we don't know. A child might gaze at the sky and not even know what stars are. Later they learn, but then new layers of mystery unfold. What are stars made of? How did they form? The questions grow with the answers. This is the engine of discovery. Our ignorance is vast, but it is the dark canvas on which we paint our understanding. Imagine if every answer were handed to us complete. We'd have knowledge, but no journey, no adventure. It is the chase, the pursuit of truth, that often gives us purpose and joy. The moment of revelation, eureka, is sweet, but it is earned by the long not knowing that came before. And so, even as we strive for answers, we can find peace and wonder in the open questions. The cosmic mystery isn't something to be sad about. It's something to celebrate. It means we are intimately connected to a universe that is richer and more profound than our current imagination. It means there will always be new horizons to seek, new truths to uncover, or at least ponder. Picture yourself under the night sky again, as in the beginning. The stillness of the air, the silent twinkling of ancient starlight. You feel the the immensity above and around you. In that moment, you are aware of a grand ignorance. You don't know what all is out there, or why it exists, or if someone might be looking back. Yet you are also aware of a profound connection. You are made of this universe's elements, your bones calcium from long-dead stars, your blood carrying iron forged in supernovae. The very act of you wondering ties you to the cosmos. Your questions are like a bridge between your mind and the infinite. Yes, the void is silent, but in our minds, that silence begets a quest. We fill the quiet with our inquiries and our explorations. We send out spacecraft, like extending our senses to the planets and beyond. We smash particles to glimpse creation's most microscopic secrets. We invent mathematics to describe black holes and quantum waves. We contemplate philosophical implications of time and existence. These are our conversations with the cosmos, and though it may not answer in words, it answers in wonders. We find one day a new kind of particle, or see a new kind of galaxy, or decode a new signal, and that is the universe's reply, telling us a little more of its story. Perhaps the universe also answers through our own self-discovery. The more we learn about nature out there, the more we reflect on ourselves. We realize how precious life is, seeing how hostile most of space can be. We see Earth from space, a pale blue dot, and it triggers a global awareness of unity and fragility. We understand that we are but one species among many, on one planet among many, in one galaxy among billions. This perspective can evoke humility and also a sense of fellowship with all existence. In cosmic timescales, human civilization is just a blink, and an individual life not even a flicker of a star. But to us, our lives are everything. They are our personal universe of experience. The big cosmic mysteries often reflect in microcosm in our personal mysteries. We wonder what our purpose is, how our minds work, how to find meaning in the vastness. And the answers are not handed to us. Each person, in a way, lives their own questions and gradually, hopefully, lives into answers. In that, we mirror the cosmos. Each of us begins in the darkness of not knowing, and along the way, we gather light. The process is continuous and perhaps infinite. In the end, after traversing all these wonders, from the birth of the universe to the nature of space, from dark matter to consciousness, we come back to a simple human truth. To not know is to be alive. Our ignorance is not just an absence. It is the driving force that keeps us searching, learning, striving. As long as there are things we don't know, we wake up in the morning with curiosity burning in our hearts. As long as mysteries abound, we have reason to marvel and reason to push boundaries. Imagine a final theory of everything that answers all possible scientific questions. Would curiosity die? Perhaps it would shift inward or to new realms, like creating art or simulated universes. But as long as we retain any sense of wonder, we find new questions. Even if somehow we understood the entire physical workings of the cosmos, we might still ask, why is there something rather than nothing? Or, what is the ultimate meaning of it all? Those questions might never have definitive answers. They're asymptotes we approach but never reach. And so we will always, in some sense, not know, and thus always be reaching, always growing. This endless pursuit is a beautiful thing. It means we are participants in a cosmic story of discovery, not just passive beings. The universe is not a static riddle to solve and be done with. It's a living conversation. Today's unknown will be tomorrow's known, and tomorrow's known will open up another unknown beyond. We stand on a threshold at all times. Behind us is knowledge hard won. Before us, the ocean of mystery. And isn't that what makes life and the cosmos endlessly fascinating? If the universe were small and simple enough for us to easily grasp in totality, it might lose some majesty. Its very unfathomability is part of its grandeur. The cathedral of stars overhead, the equations that describe them, and the equations yet to be written all form a grand, evolving tapestry. We humans are but a tiny thread in that tapestry, yet we can observe the whole pattern and add our own embroidery. Our scientific instruments are like extensions of our senses, giving the universe new ways to look at itself. Our poems, paintings, and music about the stars are the universe expressing beauty through us. We often personify the cosmos in our musings, calling her Mother Nature, or envisioning gods in the sky, because deep down we feel that intimate connection, that we and it are one. And indeed, we are not separate from the universe. We are the universe, in the form of conscious living matter.
Thus, the questions we ask the universe, we are in a way asking ourselves. And when we find an answer, we are the universe knowing itself a little better. Perhaps that is a kind of purpose we can latch onto, to be the mind of the universe, ever awakening further. If star systems are its body, perhaps civilizations are its mind, flickering on and off in the vast epochs, maybe one day linking up if interstellar travel or communication becomes possible, forming a network of cosmic awareness. Or maybe each remains an isolated island of thought. Either way, in us, the cosmic ocean has evolved eyes and brains that can map its shores and begin to chart its depths. The journey of not knowing to knowing, and then finding even more not knowing, is likely endless. And that is good. It means our descendants, be they human or augmented or AI or something beyond, will always have new frontiers. Just as we looked at moons and said, "We'll go there," and did, they might look at other stars or dimensions or layers of reality and find ways to reach or comprehend them. Each answer: the moon is barren, Mars had water, black holes exist, spurs new questions. Could life endure on Europa? Could we terraform Mars? Can we travel through a wormhole? The quest fuels itself. Standing under the cosmic sky, we may feel small, but we are also giant in what we carry. The spark of curiosity, the flame of consciousness. The distances are huge, the mass is immense, the energy is unfathomable. Yet none of those physical things inherently produce meaning. A star doesn't seek meaning, a galaxy doesn't appreciate beauty, but we do. We create meaning by examining the cosmos and by simply living and loving within it. Our unknowing and desire to know give the universe meaning, as much as our capacity for joy and love do. In the stillness of a clear night, if you listen closely, you might imagine you hear the stars whisper. Of course, space is airless and there is no real sound, but there is a metaphorical voice, the voice of wonder that arises in your own mind as you behold the stars. That voice quietly says, "There is more, so much more." It invites you to ponder, to go further than those who came before, even if just in thought. It's the same voice that led ancient people to map constellations, that led Copernicus to propose the Earth moves around the sun, that led Einstein to envision riding on a beam of light. It's the cosmos, through the medium of human imagination, urging itself on to greater self-understanding. We do not know if we will ever find all the answers. Probably we won't, because each answer breeds new questions in an endless cycle. But that is the brilliance of it. We are alive in an epoch where mysteries abound, and likely every epoch will be such an epoch. We get to be explorers of the grandest kind. Whether we sail actual ships across space or ships of thought across higher dimensions, we are adventurers. Not knowing is the call to adventure. Curiosity is our compass. Each piece of knowledge hard won is a treasure we carry, but the treasure map always extends further. To be alive is to stand on that shoreline between known and unknown and feel the enticing breeze of mystery. It reminds us that we are part of something far larger than ourselves, and yet we belong. We belong in this universe as naturally as photons and quarks and nebulae. We fit because we evolved here and of it. The atoms in our bodies were forged in stars. When we die, those atoms will return to the earth,
perhaps one day to new living beings, or drift into space to join a new star. We are a transient pattern in a much larger flow, but while the pattern holds, we have the privilege of witnessing and wondering. In that sense, our not knowing is even comforting. It guarantees that the tapestry of existence is rich beyond measure. It means there will always be more to learn, more to experience. The cosmos will never run out of surprise and majesty. We humans sometimes fear the unknown, especially on the personal scale. The unknown future, the unknown outcomes of our choices. But we also thrive on the unknown, turning it into the known bit by bit. The key is to accept that uncertainty is fundamental to life and even to the universe. We will never have absolute certainty about everything, and that's okay. That leaves room for faith, for hope, for creativity. It leaves room for us to make choices. If everything were predetermined and fully known, existence would be like reading a book with no alternate endings, interesting perhaps, but static. With uncertainties, we write our own pages as we go. The great cosmic questions, then, are both scientific and existential. What is the universe? How does it work? Blends into, what does it mean for us? What should we do? There is no single correct answer to that latter part that science can give. But perhaps the very act of seeking answers is part of the meaning. Perhaps the growth of knowledge and consciousness is one of the universe's purposes, if such a word can be used. We often imbue purpose in things that might inherently have none, but maybe that's our role, to create purpose. If the universe was initially without meaning, we give it meaning by caring, by exploring, by marveling. And oh, how marvelous it is! This strange existence, where a primate brain can comprehend the birth of galaxies and the death of stars, where mathematics scribbled on paper can predict black holes, and then the sky shows they're real, where we can read the genetic code that links us to every creature on Earth, and yet still scratch our heads about what consciousness is, or how quantum entanglement actually operates. We solve pieces of the puzzle only to find new pieces beyond the edge. It's like an infinite game, and perhaps that is the secret. Life is an infinite game, where the goal is not to win. You can't, since there's no finish, but to keep playing, to keep the game going. In this game, every new insight is a level up, every new mystery a new quest. Eventually, billions of years from now, our sun will swell into a red giant and scorch the Earth, a reminder that even the local theatre of life has an expiration date. By then, if life from Earth is wise and ambitious, it would have spread out to other stars, preserving and expanding the chain of knowledge and being. The universe will continue to evolve. Galaxies will drift apart. Stars will exhaust their fuel. Trillions of years hence, starlight might wink out as the cosmos grows cold and dark, assuming dark energy doesn't do something even stranger like ripping space-time itself. But that is an unimaginably distant future. In the meantime, we have an abundance of time and possibilities to savor. And even in that far, cold future, perhaps the descendants of our descendants, or whatever life becomes, will have unlocked deeper truths, maybe manipulating dark matter or energy, maybe tapping zero-point vacuum energy, maybe even creating baby universes to escape into when this one grows old. We can dream far indeed. Whether those dreams come true or not, they highlight our refusal to accept limits without probing them. We always seek a way, an answer, an extension. If the universe is expanding, we figure out how to navigate it. If life is rare, we treasure it and propagate it. If knowledge is hard, we train more minds and build better tools. In the reflective silence at the end of our journey, we return to ourselves, here and now. We think of all we have pondered, a universe with billions of galaxies, mostly unknown, mysterious dark matter and dark energy, sculpting fate, black holes challenging our physics, time flowing irreversibly from an ordered dawn, quantum particles dancing an unpredictable dance, countless stars with unknown planets, and maybe unknown life, our own fragile existence with a mind that defies full understanding. It's a lot to hold in one head. So we breathe and we realize it's okay not to have all the answers. It's okay, even beautiful, that there is so much we don't know. It gives us room to be curious, to be astonished, to be human. The night sky remains as it was for our ancestors, profoundly mysterious, compellingly beautiful. We have explanations for the points of light now, suns, not God's campfires or what have you. But the experience of awe is undiminished. If anything, knowing how vast and how ancient those stars are makes the night more awe-inspiring. The knowledge and the mystery together weave the full tapestry of wonder. Science and poetry meet when we confront the sublime. In that spirit, we end not with a conclusion, but with an embrace of the open questions. The universe's narrative is still being written, and we are part of the writing. Our knowledge will continue to grow, but never exhaust the mystery, and thank goodness for that. The cosmic silence is not emptiness. It is a canvas for our curiosity and imagination. The stillness is not lifeless. It is pregnant with all that we have yet to discover. And the birth of a question is perhaps the greatest gift that the darkness gives to the light of mind. We remain, as ever, small creatures with big minds, suspended between the infinitesimal and the infinite. We seek, we find, we question again. The cosmos doesn't hand us a manifesto of meaning or a clear roadmap. It simply is. But through our not knowing and our relentless pursuit to know, we craft a meaning. In the quiet dialogue between our minds and the stars, we find meaning in the very act of seeking. And so, let us cherish the mysteries. Let us cradle our ignorance softly, not as something shameful, but as the wellspring of all fascination. When we feel that itch of the unknown, when a child asks, why, how, what's beyond, or when we ourselves stare at some deep paradox of physics and feel perplexed, let's smile. That is life, that is the universe, nudging us onward. Each "I don't know" is an invitation. As long as we accept these invitations, we are truly alive, truly participating in the cosmic story. In the vast darkness, a question was born, and from that question flowed all our science, art, and dreams. We do not know all the answers, and likely never will, but we continue, eyes open in the dark, hearts receptive to wonder. For it is in not knowing that we remain curious, and it is in being curious that we remain alive in the fullest sense. The universe, speaking through silence, asks us questions in the language of awe and mystery. Our lives are our answer, an answer expressed in exploration, in love for truth, in reverence for the unknown. In this way, to not know is not just to be alive, it is to be authentically, exuberantly alive, a participant in the grand adventure as old as time and as wide as space. So let the mysteries be, and let us embrace them. Under the silent stars, feel your heart beat with both wonder and peace. The cosmos is vast and strange, and we are an inseparable part of it. In our very inability to grasp it whole, we find our place within it, searching, discovering, and marveling. This is our endless story, the slow, poetic, immersive journey through a universe of questions. And as long as questions remain, life remains vibrant. To question is to live, and to live is to bask in the unknown, even as we reach for understanding. Indeed, to not know is to be alive. Drifting in darkness, one might assume we have entered pure emptiness, a perfect void. But paradoxically, this void is full, invisible to our eyes, intangible to our skin. An entire invisible architecture underlies the darkness. Space is not a barren stage. It is alive with unseen phenomena. First, consider the idea of space itself as something. Not just an emptiness to move through, but a fabric that can bend and ripple. Over a century ago, Albert Einstein revolutionized our understanding with the notion that space and time are intertwined and dynamic. Here in the silence, you can almost feel it. The very space around you has a texture, a geometry. You are weightless now, far from any planet's pull, yet you still sense the faint tug of gravity from distant bodies. This is because the fabric of space-time is curved ever so subtly by the mass of everything in the universe. Even where there is no star or planet in sight, space isn't flat nothingness. It's shaped by the gravity of far-off galaxies, by clusters of matter unseen but present. Extend your hand, in imagination, and try to touch the darkness. What do you feel? Nothing. And yet, not nothing. Throughout this emptiness, fields permeate. Think of a field as a kind of invisible grid that can carry energy or force. One example is the gravitational field. It extends infinitely, binding galaxies and holding you gently in the cosmos even out here. Another example, the electromagnetic field. Even where no light shines now, the electromagnetic field is everywhere, capable of carrying light across trillions of kilometers or transmitting the crackle of a distant pulsar's radio whisper. It is through this field that starlight travels. And when that light passes by a massive object, the field, and thus space itself, warps, bending the light's path. Now dive deeper. Modern physics tells us that even in a perfect vacuum devoid of all matter, quantum fields fill space. Picture, on an incredibly small scale, that the silence is broken by a constant, gentle fizz of activity. Particles flicker in and out of existence, like tiny fireflies, appearing and disappearing so quickly we can hardly say they were there. This isn't science fiction, but the strange reality of the quantum vacuum. What we call empty space is more like an ocean of possibilities, with fields for every particle, electrons, quarks, photons, and more, lying dormant like a calm sea, yet capable of excitement. By the weird rules of quantum physics, these fields flutter, creating particle-antiparticle pairs that just as quickly annihilate back into nothingness. It's a quiet dance going on all around us, utterly imperceptible on human scales, but very real nonetheless. Here, in the deep void, nature abhors a vacuum in the old saying, but not by filling it with air or ordinary matter. Instead, nature fills it with fields and potentials. In truth, making a truly empty space with absolutely nothing in it is impossible as far as we know. The cosmos always has something at play, even if it's just the subtle curvature of space-time or the low hum of those quantum fluctuations. Consider the space around your body now. Unseen particles called neutrinos are flying through you by the trillions each second, cast off by distant stars and ancient explosions. You don't see or feel them, yet they are there, ghosting through the empty space, as if it were a busy crossroad. Meanwhile, gravitational waves, faint ripples in space-time from faraway cosmic cataclysms, may be washing through this region even now, imperceptibly stretching and squeezing distances by the tiniest fraction. Space, for all its stillness, can carry these ripples across billions of light years. All these things remind us that the void is teeming, but in hidden ways. It's as if the darkness has its own heartbeat, too low or diffuse for us to detect without instruments, but very real. In deep space, sensitive instruments have picked up signs of this hidden life. The hiss of particles from the sun gradually fading into the faint crackle of cosmic rays from the galaxy, or the way a spacecraft can detect wisps of magnetic fields draped through interstellar space. Not long ago, the Voyager 1 probe, humanity's most distant messenger, slipped beyond the influence of our sun's solar wind and entered interstellar space. Out there, it heard something astonishing, a faint hum of plasma, a vibration in the very sparse gas between the stars. In the middle of what seemed like utter emptiness, there was the slightest whisper, the interstellar medium itself quietly singing on a narrow radio frequency. It was as if the void had a voice after all, hidden in electromagnetic vibrations. So as we float here, let's banish the thought that we are in nothingness. Instead, realize we are immersed in a grand, subtle structure. We are in the midst of an invisible ocean that connects all things. Space is not empty. It is a medium, not a medium like air or water, but a medium that carries light and gravity, a stage that can bend and ripple, a field of potential. If we had the right senses, the darkness would light up with activity. We might see the gentle curvature like dim swirls in black glass, hear the soft static hiss of particles popping in and out of existence, or feel the tug of far-flung masses moving the fabric under us. The silence and darkness remain, but now we know the truth. Behind them lies complexity and structure. The void is alive with fields, and those fields cradle us even as we drift. The emptiness, ironically, is full. Having opened our minds to the living void, we can now carry onward. With respect for the unseen tapestry around us, we begin our outward journey from Earth, a journey that will take us through successive layers of cosmic emptiness, each revealing new wonders hidden in the dark. From home into the dark, leaving Earth's embrace. Our journey truly begins now. Picture Earth below you, a tender blue glow haloed in sunlight against the black of space. As we depart our home, we leave behind the last familiar sounds, the whisper of wind, the murmur of human life, even the faint radio chatter from civilization. As we rise above Earth's atmosphere, the air thins and the sky darkens from blue to indigo to black. The comforting blanket of atmosphere that carries sound is gone. The silence of space welcomes us fully, and the only remaining voice is the quiet hum of our spacecraft systems, or perhaps our own breath in the suit. Look down one more time at that lonely speck of a planet, shining against the cosmic night. It is astonishing how small the cradle of all humanity appears against the backdrop of the universe. In a few hours of imagined travel, Earth shrinks from a vast globe to a bright bluish star, then merges with the brilliant point of the sun. Soon, the inner solar system becomes a memory, a faint glow of our star with tiny pinpricks of planets that quickly vanish into the sun's glare. We glide past Mars's orbit. The ochre dot of the red planet recedes behind us. We pass mighty Jupiter, its banded clouds and great red spot just visible for a moment as a striped marble before it too is lost in the distance. We catch a last glimpse of Saturn's rings shining like a delicate halo. Then Saturn fades. Uranus and Neptune, pale blue twins, slide by one after the other, bidding us farewell with their cold, reflected sunlight. Each world's departure marks our ship's steady progress into the deep. With each passing planet, the sun's light dims slightly more, its warmth weakens. The solar system's glow, the bright stage of humanity's entire story, is shrinking behind us, turning into just one more star in the sky. Out here, sunlight is no longer the fierce golden flood we know on Earth. It has faded to a gentler, distant gleam. With each 100 million kilometers we travel, the sun diminishes, its rays growing weaker, until it is but an intense star among others, no longer blindingly bright. The warmth that once caressed our face on a summer day is now diffused. In shadows, the cold of space encroaches quickly. We are headed toward the edge of the solar system, a frontier not marked by any solid barrier, but by a change in the very environment around us. As we glide beyond the orbits of the outer planets, we cross through a diffuse realm of ice and rock, the Kuiper Belt, home to dwarf planets like Pluto and countless comets circling in the dark. These ancient frozen remnants occasionally catch a glint of sunlight, but mostly they drift unnoticed. Imagine passing one, an irregular chunk of ice and dust floating alone, sunlight just barely painting one side in a dim grey glow, the other side in perpetual night. This far from the sun, space takes on an even deeper black. Turn your gaze away from the sun's direction, and the sky is a rich spray of stars on velvet in every direction. Finally, we approach the heliopause, the boundary where the influence of our star wanes. Here, the solar wind, a stream of charged particles blowing outward from the sun, slows and collides with the sparse gas of interstellar space. It is the edge of the sun's protective bubble, the heliosphere, and beyond it lies true interstellar space. The Voyager 1 spacecraft crossed this boundary in 2012, and for the first time, a human-made object tasted the interstellar wind. Now we, too, symbolically cross this invisible threshold. The particle density around us drops even further. The breeze of particles from our sun gives way to an even fainter presence. The faint traces of gas, dust, and cosmic rays that fill the galaxy. Pause here for a moment. We are at the frontier of our solar system, tens of billions of kilometers from home. If you look back, you might just catch Earth's distant starlight glimmer, reflecting a bit of sunlight, perhaps not even visible without aid. All the planets we know are behind us now, clustered near that tiny sun. Ahead lies a gulf so vast our measures of distance strain to describe it. If we were truly aboard a spacecraft, this is the point where the sunlit solar system ends and the long night of interstellar space begins. Here, the silence deepens. We shut off our engines to drift and listen. Without the solar wind's charged particles zipping by, there is less hiss in our instruments. The void seems even quieter. We have left behind the last echo of Earth's radio broadcasts. They are still racing outward at the speed of light, but here even those signals are too faint to detect easily. It dawns on us. We are really, truly beyond the realm of the familiar. We stand, or rather, float, in a darkness that no human eye has directly beheld, with only our imaginations and robotic pioneers to guide us. Slowly, as our ship coasts further outward, the sun diminishes to a mere pinprick of light, no bigger or brighter than an ordinary star. We are now effectively in midnight, that is the same in every direction, a true 360-degree night with no sunrise to come. How does it feel? There is a serene yet disquieting beauty. The starry sky is breathtaking. With the sun's glare gone, we see more stars than ever before, a dusting of diamonds on black velvet in every direction. The Milky Way forms a gauzy band of light, the combined glow of billions of distant stars in our galaxy's disk. Amid these stars lurk faint hazy patches where interstellar dust blocks light beyond, making dark nebulous silhouettes. We have one more layer of our solar system to traverse, the hypothetical Oort cloud, a vast spherical halo of comets that may extend a quarter of the way to the next star. These cometary ice balls are so spread out that we might not see any as we pass. They are like solitary snowflakes drifting miles apart. Statistically, we move through this region without encountering a single object. The distances are simply too great. When we finally emerge from this cloud, we'll be traveling physically. It would take many centuries or millennia at typical spacecraft speeds. The sun relinquishes us entirely. We are no longer bound to our home star. We are, for all practical purposes, between the stars. An overwhelming realization might strike us here. The scale of what we've crossed. It took us hours or days to leave the planets behind, but it would take years upon years to traverse the Oort cloud, and beyond that, many more to reach even the nearest star. And this is still just our cosmic neighborhood. The gap between stars is enormous and mostly empty, mostly, but not completely. As we venture onward, we carry with us the knowledge that emptiness is never absolute. Into the interstellar void, an ocean between the stars. Now we sail truly in interstellar space, the space between the stars. The nearest stellar neighbor to our sun, Proxima Centauri, lies unimaginably far ahead, over 4 light-years. If we continued on our craft at speeds far beyond what we currently achieve, it would still take many decades or centuries to reach it. The distances are so vast that for long stretches, it will seem we are going nowhere, surrounded by unchanging darkness. This is the oceanic gulf that separates star from star, and it is here that the character of deep space fully reveals itself. The interstellar void is often described as emptier than any vacuum we can create on Earth. There are essentially no large objects here, no planets or asteroids or moons, just the exceedingly sparse interstellar medium, a wispy mix of gas atoms, mostly hydrogen, and the occasional dust grain. On average, each cubic meter of space might contain only a few atoms of matter. Picture that, a volume of space the size of your living room with maybe one lone atom drifting through it. By comparison, that same volume of air on Earth contains on the order of 1025 molecules. The emptiness out here is almost absolute. And yet, as we've learned, it is not truly absolute. Those few atoms, those stray particles, matter on cosmic scales. It's cold out here, but not completely frozen. We'll discuss the exact temperature of space soon. For now, note that any atom drifting here is likely moving very fast, energized by shock waves from distant stellar explosions or cosmic rays that streak through. The interstellar medium can actually be quite energetic in places. Tenuous gas can be heated to millions of degrees by supernova remnants, so thin you wouldn't feel heat, but the atoms themselves zip about furiously. Elsewhere, there are colder, dense pockets, molecular clouds, but those are relatively rare and far between. Mostly we traverse a quiet, diffuse haze. Every so often, as we journey, we might encounter a region with slightly higher density of material, perhaps skirting a tenuous nebula or brushing the edge of a spiral arm of the galaxy. Our Milky Way is structured. Its spiral arms contain concentrations of gas and dust where new stars are born. If our path takes us through one of these subtle structures, we might notice the stars around us, temporarily fewer as dark nebulas block them, or detect a faint increase in particle hits on our sensors. But then, like a ship leaving a patch of fog, we emerge again into clearer space. There is also radiation everywhere. We left behind the sun's intense radiation, but now we are bathed in a gentle rain of cosmic rays, high-energy protons and nuclei that zip through the galaxy at nearly light speed. They come from distant supernovae and energetic events scattered throughout the Milky Way. They silently pierce our spacecraft's hull, each a tiny subatomic bullet from some far-off celestial rifle. We don't see or feel them directly, but detectors would register little sparks as these cosmic rays pass through. Additionally, every now and then, a flash of lightning in the void. Not literal lightning, but an electromagnetic burst from something like a flaring star or a magnetar's distant pulse. We are too far to feel any direct effect, but our instruments might catch a blip of X-rays or gamma rays, brief reminders that even in emptiness, events happen. One might think nothing ever happens in interstellar space, but nature occasionally reminds us that even here, things occur. For example, shock waves from a distant supernova can traverse the void, a shell of slightly denser, hotter plasma expanding outward. If our ship were overtaken by such a front, extremely unlikely in our short travel window, we'd notice a sudden spike in particle density and radiation, as the shock wave, diluted though it is by distance, washes over us. It would be a reminder that even the silent sea of space has weather of a sort, cosmic weather, measured not in rain or wind, but in surges of radiation and gusts of charged particles. As we travel, let's imagine we cross paths with something unexpected. The chances are minuscule, but the galaxy is vast and full of surprises. Perhaps we encounter a lone fragment of a comet or a rogue asteroid drifting, debris from some ancient encounter that was flung out here. More intriguingly, perhaps we detect the faint gravity or slight dimming of starlight indicative of a solitary star wandering the interstellar depths. Yes, a few stars have been kicked out of galaxies at tremendous speeds, destined to roam the space between galaxies forever. Or we might come across an interstellar cloud, a region where the gas is a bit denser, enough to form a nebula visible if illuminated by starlight. In our mind's eye, perhaps we alter course to skim the edges of such a ghostly nebula, its filaments glowing dimly blue or green from the light of embedded newborn stars. It would be a rare sight, tendrils of gas forming faint, intricate swirls against the darkness, like gauze lit from within. These clouds are the nurseries of future stars, though the process takes millions of years. Passing by one, we witness a balance of emptiness and substance. From a distance, the cloud is nearly invisible. Up close, you realize it's made of extremely tenuous gas that nevertheless, given enough of it, can birth brilliance. Without an external reference, it's easy to lose track of motion, but we are indeed moving, perhaps drawn subtly by the gravity of the nearest star ahead, or simply coasting on the momentum we had leaving the solar system. Let's orient ourselves. The nearest star system, Alpha Centauri, of which Proxima is a member, is a bit more than 4 light-years away from Earth. That's the distance light travels in over 4 years, roughly 40 trillion kilometers, an almost unfathomable gulf. If our ship somehow could travel a significant fraction of light speed, it would still take years to get there. At more realistic speeds, many millennia. And presently, in our poetic journey, we're not moving nearly that fast. We are drifting contemplatively. This emphasizes the sheer breadth of emptiness. Even at tremendous speeds, the journey between stars stretches longer than entire human lifetimes. And currently, we have chosen a path not directly toward any star, but out of the galaxy, meaning our journey in interstellar space will last even longer, essentially indefinitely, unless we aim for another galaxy, which is vastly farther still. Between us and the next galaxy, Andromeda, 2.5 million light-years away, there may be absolutely nothing large. The interstellar and eventually intergalactic distance is often just vast space with the occasional wandering atom or photon. No islands in the void, aside from those potential rogue objects we mused about, which themselves are extraordinarily few and far between. The darkness here is profound. If we turn off all the lights on our ship, the view is stark and primal. Without a nearby sun, space is nearly black to our eyes, except for the stars. And those stars, though numerous, do not illuminate our surroundings. Their light mostly travels on without hitting us unless we look directly at one. You could hold your hand in front of your face and not see it at all. There is no ambient glow, only the sharp rays coming from each distant star. If your hand isn't in one of those direct rays, it remains invisible, swallowed by black. That's an utter darkness few have experienced, since even on Earth at night, the atmosphere and environment scatter some light. Here, shadow and light are absolute. If we allow ourselves a moment of vulnerability, it's a bit unsettling. You truly are an entity in almost pure void, with only distant pinpricks of starlight around. This segment of our journey might feel uneventful, but in its quiet way, it teaches us a truth. The isolation of celestial islands, stars and their systems, is profound. Stars are like cities, separated by vast, uninhabited wilderness. We are traveling through that wilderness now. It humbles any traveler. We begin to sense why the night sky evoked such awe in our ancestors. Those stars are both tantalizing and unreachable beacons across a sea of nothing. As we continue toward the deeper reaches of our galaxy, or rather, out of our galaxy, we have set a course aiming above the galactic plane, seeking to exit the Milky Way. We prepare to encounter something that will bring many of these abstract concepts into a tangible form. A lonely world adrift in this sea of night, a rogue planet. Before we leave the domain of starlight entirely, we might cross paths with one of these drifting worlds. It will give us a direct experience of what it means to exist in deep space without the light or warmth of a sun. a piece of solid matter enduring the cosmic night. Let's approach this silent, cold traveler next. Rogue planet, a lonely world, adrift in darkness. In the beam of our spacecraft's spotlight, something solid materializes out of the eternal night. A planet, but one with no star in sight. We have found a rogue planet, a wanderer in interstellar space. It's a world cast out from its parent star system long ago, now doomed to roam the galaxy in perpetual darkness. Our instruments first detect it not by sight, it's virtually black on black, but by a subtle gravitational tug and a slight blurring of background starlight, signs that a massive object is near. We angle our ship toward it and shine powerful floodlights to illuminate the surface as we draw closer. Imagine shining a flashlight into a dark ocean and revealing, in the void, the outline of an island. That is what this feels like. The rogue planet's surface slowly comes into view. Perhaps it is a rocky, frozen world, its surface coated in frost, or it could be a gas giant with faint, ghostly cloud bands visible in our spotlight. For concreteness, let's assume it's a rocky planet, somewhat larger than Mars. The surface is an expanse of ice and rock. Long, jagged cracks run across plains of frozen water or ammonia. If it once had an atmosphere, much of it may have condensed and frozen onto the ground in crystals that glitter in our lights like tiny stars on the surface. There is no day-night cycle here. The entire planet is in endless night. Only the faraway stars speckle its sky. They would appear as one might see from any dark location. Though without a sun, even the nearest stars would provide negligible illumination. If the planet has no atmosphere, the stars wouldn't twinkle. They'd be pinpoints in a stark black firmament. And they do not move through a night. The concept of a day or year has lost meaning without a sun to orbit or spin around in light. The planet might still rotate, but there is no sunrise, no sunset, just constant night, aside from our ship's transient lights. What is the temperature on the surface? Almost certainly near absolute zero, just a few degrees above it. Perhaps slightly warmer if the planet has internal heat left over or radioactive decay warming its core. But on the surface, any air or water is frozen solid. If there were an atmosphere once, it likely collapsed into frost and thin layers of ice on the ground when starlight vanished. A world like this is presumably geologically dead on the surface, although who knows, deep down there could be some warmth. Imagine stepping onto this world. You plant your boot on ground that has perhaps not felt a single touch in billions of years. Your suit's headlights cast long, sharp shadows over an alien terrain that has never known natural light. The ground crunches as you walk, possibly a mix of frozen gases and regolith. If there were any wind once, now there is complete stillness. If there were any life in the distant past, it likely perished or retreated deep below. The environment is as harsh as it gets, a cosmic winter that never ends. Look up from this rogue planet's surface. The sky is full of stars, likely breathtakingly so. Unpolluted blackness with the Milky Way arching overhead as a misty band. Without a sun of its own, the planet's sky knows only the light of other suns. If it has a moon or two, conceivably, if they were also ejected together, you might see their dark forms or faint reflected starlight as they drift, but nothing like the bright face of our moon. Centuries ago, the French philosopher Blaise Pascal wrote of the eternal silence of infinite space, filling him with dread. That sentiment resonates even now. The vast emptiness can test the courage of anyone. Standing on this rogue planet, you feel that eternal silence viscerally. The only sounds are your suit's breath and perhaps the crunch of your footsteps. The only light is what you bring. It is a tableau of utter isolation. Yet even here, one can find a strange beauty. The planet's frost-laden rocks sparkle under our lights. The stars above are unwavering and brilliant. Perhaps a distant nebula or the glow of the Milky Way's core adds a faint cloudy sheen in one portion of the sky. This world, though lonely, is part of the galaxy and shares in the grand cosmic panorama. Astronomers suspect there could be countless such orphan worlds in our galaxy, possibly even more free-floating planets than there are stars. Some might be gas giants, still slowly cooling from their formation, perhaps emitting a faint infrared glow from leftover heat. Others could be smaller, rocky bodies like the one we tread upon. If a rogue planet is large enough and had enough internal heat, it might retain a blanket of atmosphere. In rare cases, that internal heat, from radioactive decay or residual formation energy, could keep a subsurface ocean liquid beneath an insulating crust of ice. One can only speculate, but it's tantalizing. Could some form of life survive around hydrothermal vents on a rogue world's deep ocean floor, never seeing starlight yet eking out a living on geothermal energy? It sounds like science fiction, and likely is, but it highlights how the darkness, while harsh, might not be absolutely devoid of all possibility. For now, on the surface of this silent planet, there is no obvious life. We might find organic molecules or the frozen remnants of what was once an atmosphere. But nothing moves save ourselves. Nothing changes. Our presence is a brief spark of warmth and activity on a world that will soon revert to inert silence when we depart. We take a last look around. In a sense, this planet embodies many themes of our journey: isolation, cold, and darkness, yet also resilience. It continues along its lonely path regardless, a planet without a sun, carrying on through the night. In our short visit, we've brought a bit of light to it, literally illuminating what was hidden. But as we leave, it will recede into darkness again, continuing its quiet voyage around the galaxy's center. We board our craft and lift off. Our lights play over the craggy horizon one last time, then we angle away. The rogue planet grows small behind us, eventually becoming just another dark lump, invisible in the Black Sea. It will remain silently traveling, perhaps for billions of years, until maybe one distant day, purely by chance, it is captured by a new star or encounters another object. Most likely, it will wander forever. After experiencing an object so profoundly alone, our spacecraft, with its warmth and light, feels like a haven by contrast. We have the means to illuminate and understand our surroundings. We carry our environment with us. That little world had no such fortune. It must endure the cosmic night alone. Now, we set our course outward once more. Having encountered a solitary planet, we refocus on the larger journey, leaving the galaxy itself. Ahead, the stars begin to thin out. We are moving toward the edge of the Milky Way. The glow of the galactic plane, that river of stars, is getting fainter and narrower behind us. Before fully exiting, let's prepare by reflecting on how we know what lies ahead in the vast dark between galaxies. One key tool has been the phenomenon of gravitational lensing, which we touched on indirectly with the rogue planet, its gravity-bending starlight, and earlier in concept. It's worth pausing to appreciate how gravity in the dark can reveal the unseen, before we venture into the truly sparse intergalactic void. Gravity's invisible lens, revealing the unseen. Before we leave our galaxy entirely, consider one more marvelous phenomenon, one that has been a silent companion in our exploration of the dark: gravitational lensing. It's the cosmos's way of letting gravity, even from invisible things, bend and play with light, creating natural telescopes and funhouse mirrors in space. Imagine observing a distant galaxy, billions of light years away. Normally, you'd see its faint smudge in the sky, and that's it. But if a massive cluster of galaxies lies in the line of sight between us and that far galaxy, something extraordinary happens. The cluster's gravity warps the space-time through which the distant galaxy's light travels. The result? We might see that single distant galaxy appear multiple times, or its image smeared into a curved arc of light, or even an eerie ring encircling the foreground cluster. Such a ring-like image is aptly named an Einstein ring, after Einstein, whose general relativity predicted this gravitational light bending. We encountered this concept up close near the black hole, where warping was so strong light could loop around. But gravitational lensing often happens on larger scales with galaxies and clusters acting as lenses. It is one of our most potent tools to map dark matter. Why? Because dark matter doesn't shine or reflect light, but it does have gravity. When we observe distorted, lensed images of background galaxies, we infer the presence and distribution of mass, including dark matter, in the lensing cluster. In fact, some of the clearest evidence of dark matter's existence and layout comes from noticing that lensing patterns demand more mass than visible galaxies provide. Consider the famous image of the Abell 2218 galaxy cluster. Photographs show numerous orange-yellow cluster galaxies and, amid them, strange stretched blue arcs. Those arcs are distant background galaxies whose light has been bent and magnified by the cluster's gravitational field. It's as if the cluster were a giant piece of curved glass, warping their image. For a listener, what's intriguing is that gravitational lensing lets us see heavy things that are otherwise invisible. A black hole drifting in front of a background star can momentarily make that star appear brighter, a phenomenon called microlensing, because the black hole's gravity focuses the star's light toward us. In our journey, had we not known the black hole was ahead, we might first have noticed it by the distortion of starlight around it, stars seeming to smear and form rings around an unseen center. Even on huge scales, entire regions of dark matter in the cosmic web have been mapped via weak gravitational lensing, statistically analyzing tiny distortions in the shapes of thousands of background galaxies. By seeing how their shapes are coherently sheared, scientists can reconstruct the hidden mass distribution in front of them. It's akin to looking at a distant grid of lights through an uneven window pane. By the distortions of the grid's appearance, you discern the shape of the otherwise invisible glass. Gravitational lensing not only confirms dark matter's presence, it also produces some of the most awe-inspiring visuals in astronomy. The Einstein cross, for example, is a single quasar, a bright galactic nucleus, far away that appears as four identical star-like images arranged in a cross around a foreground galaxy's center. The galaxy's gravity splits the quasar's light into four. For a long time, this was one of the evocative proofs that gravity can mimic magic, one object appearing in multiple places at once. During our travels, if we had looked toward a massive galaxy cluster from just outside our galaxy, we likely would have seen such lensing arcs ourselves, slivers of light from galaxies hidden behind the cluster, made visible by gravity's lens. It's a beautiful reminder that even though space is dark and light travels straight, the shape of space itself can curve and reroute light, effectively letting matter paint with beams of brightness. To imagine it without visuals, picture walking in a dark forest at night with a lantern, the background galaxy. If there's a clear, curved piece of glass hanging invisibly in the air, the gravitational lens, you might suddenly see your lantern's glow form a ring or appear in strange patches on the trees around, even though there is only one lantern. You might not see the glass, but you know something powerful is there from the way your light behaves. Thus, gravitational lensing has been a hidden ally in exploring the dark. It assured us that unseen mass was truly there when we discussed dark matter. It created spectacular light shows near black holes and massive clusters, and it demonstrates vividly that gravity operates even in darkness, bending light itself to its will. The darkness can therefore produce illumination, not by emitting it, but by sculpting its path. In a broader sense, gravitational lensing shows how interconnected things are. A galaxy's image can be affected by another cluster millions of light years in front of it, which in turn is shaped by an even larger structure's dark matter. The universe is layered. The light from the deep past passes through the structures of the later universe, carrying with it the imprint of everything in between. By the time it reaches our telescopes, That single beam of light has interacted with the gravity of stars, galaxies, and invisible mass lumps, telling a story in its distortions. As we prepare to leave the confines of our galaxy, gravitational lensing stands as one last example of a theme we've seen repeatedly. The invisible can be inferred and even visualized by its influence on the visible. In the grand dark tapestry of space, gravity is one of the threads connecting the seen and unseen, revealing the latter through subtle effects. It's a final piece of evidence that in the cosmic dark, absence often hides presence, whether it's hidden mass or an entire hidden truth about the structure of space-time. And with that understanding, we feel even more prepared as we plunge into the sparsest expanse yet, the gargantuan void between galaxies. The void between galaxies, intergalactic space, and the cosmic web. We engage our conceptual engines and leap onward, leaving the Milky Way's bright throngs of stars behind. Time and distance blur as we traverse tens of thousands of light years, rising above the galaxy's disk. At last, we find ourselves outside our home galaxy, looking back at it from a vantage point in intergalactic space. The Milky Way floats in our field of view, a majestic spiral, its whirling arms and central bulge, luminous with the combined light of hundreds of billions of stars. It is an island of light in a sea of darkness. Nearby, we see another haze of light, the Andromeda Galaxy, our big neighbor, about 2.5 million light-years away, visible as a small smudge even to the naked eye from Earth, and from here, still just a modest ellipse of light. Scattered around are a few smaller fuzzy patches, satellite galaxies and distant members of our local group. We are now in intergalactic space, the space between galaxies. If interstellar space was an incredible vacuum, intergalactic space is even closer to pure nothing. The intergalactic medium, IgM, is even thinner than the interstellar medium. On average, in each cubic meter of intergalactic space, there might be only one atom or less. It's hard to convey such emptiness. In a cubic kilometer out here, there might be only a handful of particles. This is far emptier than even the best laboratory vacuums ever achieved. We have reached a level of near nothingness that challenges the imagination. If we turn in all directions, what do we see? The sky here is darker than ever. With the naked eye, even superbly dark adapted, you might see only the faint glow of our Milky Way behind us and Andromeda ahead, and a sprinkling of other distant galaxies as tiny, faint smudges of light if you know where to look. Everywhere else, blackness. But if we allow our eyes or instruments to integrate light over time, gradually we'd pick up an almost ghostly background glow. Innumerable remote galaxies too faint individually to register, plus one more thing, an all-pervading faint microwave glow, the cosmic microwave background, CMB, the afterglow of the Big Bang, coming from every direction. Our eyes can't see microwaves, but a suitable antenna would find the entire sky gently aglow at about 3K, just as we discussed earlier. Yet even here, as always, not empty holds true. The intergalactic medium contains matter, mostly extremely thin, hot plasma. In the spaces between galaxies within clusters, the IgM is hot enough to emit X-rays, temperatures of millions of degrees, though so dilute you wouldn't feel it. In the great cosmic voids, it's cooler and even more diffuse. But also, intergalactic space contains dust, albeit in almost vanishingly small amounts. Over eons, galactic winds from starbursts and quasars have blown a little dust out of galaxies. You might find a solitary grain of carbon or silicate drifting here. Ashes of long dead stars spread thin across cosmic gulfs. These dust grains are so few and far between that one could travel for light years and not encounter a single mote. Yet across the vast volumes, their existence can be inferred. For instance, they very slightly redden the light of faraway objects or produce a faint infrared background glow. Collectively, the sparsely distributed gas in intergalactic space still accounts for a great deal of normal matter. In fact, Astronomers found that a significant fraction, perhaps half, of all the atoms in the universe lurk in these nearly empty intergalactic filaments and sheets, the so-called missing baryons that don't reside in galaxies. It's poetic. The most desolate expanses still hide much of the universe's ordinary matter in a form so diffuse it eluded detection for decades. One could drift here for 1 million years and perhaps not collide with even one stray dust grain or atom. That's how empty it is. Yet we know this subtle medium is there, because when we look at distant quasars, we see their light very slightly dimmed, or bluer light slightly absorbed at specific wavelengths by traces of intergalactic gas. Space, even here, has an extremely tenuous weather. If an astronaut were here, far beyond any galaxy, floating in suit, what would they physically feel? Essentially nothing. No air, of course. No sense of wind or pressure or temperature in the usual sense. The temperature of space here, defined by the cosmic background radiation, is about 3 degrees above absolute zero, roughly 270 degrees centigrade. Any object left alone out here would eventually cool to that temperature by radiating its heat away. In practice, an astronaut in a suit, shielded from sunlight, would radiate away body heat and slowly cool, but would likely die from lack of oxygen long before reaching the ambient temperature. The concept of hot or cold becomes tricky when there is almost no matter to measure it. The medium here can be simultaneously extremely hot in one sense. The few particles can be moving with lots of energy, yet cold in another. There are so few particles that they won't convey heat to you. It's correct to say the effective temperature of the void is just under 3 K, set by that bath of leftover Big Bang light that fills the cosmos uniformly. If you had microwave eyes, you'd see the whole sky aglow with that faint 3 K afterglow. It's almost uniform in every direction, a gentle whisper of long-ago fire that has cooled over 13.8 billion years. The differences across the sky are minuscule, on the order of 1 part in 100,000. The void here is as cold and homogeneous as the universe gets naturally. Now reflect on how far we've come. We have left behind not only Earth and the Sun, but every star of our galaxy. The Milky Way now is just one object in the sky, a hazy oval of light behind us. Andromeda is another. The rest of the universe lies beyond, all around. If we look farther outward, beyond the local group, we see other galaxies, perhaps the pinwheel, the whirlpool, giant ellipticals in the Virgo cluster, tens of millions of light years away, each just a faint smudge, needing a telescope to discern structure. Many of those galaxies are grouped into clusters and superclusters, interconnected by filaments of dark matter and gas, and separated by giant voids with hardly any galaxies at all. We are at a vantage point where the cosmic web, the large-scale structure of the universe, can be contemplated as a whole, filaments and clusters and vast empty cells in between. We might find ourselves drifting near one of the largest cosmic voids. In such a location, the nearest galaxy might be tens of millions of light years away, just a tiny swirls of light in one region of the sky. The rest would be mostly black, dotted with faint galaxy images. It would be perhaps the loneliest location in terms of visible landmarks. In such emptiness, an unsettling thought arises. How would a human mind fare here for long? We are about to consider that as we turn inward for a moment, but before that, let's marvel at the panorama one last time. If we look back at our Milky Way from here, we see it in its full glory, a sideways-on spiral with a bright core and tenuous arms. We see its dusty disk obscuring some light, its central bulge glowing. We realize our entire solar system was nestled in one of those arms, so far inside that from there we could never get this view. We had to leave it to truly see it. Looking outward, we behold our local group's members scattered, and further out, we sense the pull of the Virgo cluster, the massive cluster of galaxies that is the center of our larger supercluster.
which scientists have named Laniakea, meaning immense heaven in Hawaiian. Our galaxy and Andromeda and hundreds of others are flowing together toward that region, drawn by gravity, something we'll touch on when we discuss the great attractor shortly. For now, in this floating moment outside the galaxy, it's time to address a different pull, the tug on the human heart when faced with such infinite silence and isolation. We have been bold explorers, but we are also flesh and thought, and the psychological toll of deep space is a story of its own. Before continuing to the next grand cosmic structure, let's turn inward to reflect on how profound darkness and distance might affect a human mind and spirit. Alone in the abyss, the psychological toll of deep space. Let's step away from the physical marvels for a moment and consider ourselves tiny, sentient beings in this enormity. We have crossed unimaginable distances, surrounded by eternal night and silence. Now, contemplate the human experience of such an environment. What would it feel like to truly be out here, with no familiar sky, no ground beneath you, no nearby sun to mark the days or give you warmth? Even the most seasoned astronauts, who travel merely to the International Space Station or to the Moon, always had Earth glowing nearby, a bright oasis of life in the void, which gave them comfort and orientation. But push beyond. Say an astronaut on a mission to Mars faces a tiny distant Earth, a mere bluish dot, which can already induce a profound sense of isolation. Take it further. Imagine an explorer in a spacecraft, leaving the solar system entirely, watching the sun dwindle to a sharp point of light among others. That mental picture alone, the sun as just another star, has made many a science fiction story haunting, because it touches on our deep-seated need for connection and reference points. Now extend to our scenario. No sun at all, no Earth, no planets, just your ship and the universe. You are the only warm thing for trillions of kilometers. The nearest known anything is maybe a star so far away it's just a speck. This scenario is beyond any isolation a human has ever experienced. How does one cope? On Earth, we have cycles of day and night, weather, the rhythm of life, other living beings around. In deep space, there is no natural rhythm, except maybe the oscillations of your ship's systems or your own heartbeat. Time can blur. Eternal night can play tricks on your perception of time's passing. Without a sun rising and setting, an hour or a day becomes an abstraction you must impose artificially by clocks and routines. The psychological challenge would be immense. Loneliness and boredom could become overwhelming, even if one is surrounded by the wonder of the cosmos. There's a reason explorers throughout history often traveled in crews. Few venture completely alone for long periods, because isolation can weigh heavily on the human psyche. History offers glimpses. Adventurers in polar winters, submariners deep undersea, or test pilots on solo flights have reported distortions of time and mood swings in prolonged isolation and darkness. Centuries ago, Pascal, whom we quoted earlier, admitted that the infinite silent spaces terrified him. That fear is a deeply human response to confronting a vastness in which we seem so insignificant. An astronaut alone in intergalactic space might undergo phases of awe and inspiration, followed by waves of anxiety or even existential dread. One moment you might feel at one with the universe, a transcendent unity with this beautiful dark cosmos. The next moment, you might feel unbearably small and alone, like a child lost in a black desert that extends forever. Our traveler would have to find meaning and stability internally. They might cling to routines, exercise, maintenance, observations, to structure time. They might have photographs of home, recordings of voices or music to provide some emotional connection. Perhaps they'd have a communication link still active to mission control, though with increasing delays as distance grows, until it becomes impractically long, and beyond our galaxy,
Essentially, no communication with home would be possible due to distance and eventual lack of powerful enough transmitters. We can imagine the profound homesickness one might feel, seeing the Milky Way from outside, realizing all of humanity and history is contained in that faint glimmer, and you are out here, separate. The overview effect that astronauts feel, a cognitive shift when seeing Earth as a small, fragile ball in space, would be magnified to an extreme. Not only Earth, but the entire galaxy would be seen as one small thing among many. Our explorer might have an incredible intellectual understanding of unity. All people, all known life, are truly together on one tiny island, but also a sobering sense of cosmic solitude. There is so much emptiness, and I am out here in it. Will future explorers venture this far, and what will they feel? Perhaps by then, technology, like advanced AI companions or virtual reality simulations of Earth environments, will help. But nothing can change the reality outside the hull. Silent, star-speckled darkness in all directions. Interestingly, some humans might adapt and even thrive in such an environment. There can be a peace in solitude. The absence of noise, of crowds, of conflict. A person might find a monastic calm to contemplate existence. They could spend hours stargazing with eyes or instruments, meditating on the nature of things, writing poetry about the stars. The awe can be a powerful salve to fear. Knowing what we know about the universe's workings could also be comforting. You're alone, but you're not lost. You understand where you are and what that darkness is. Not demons or chaos, but physical space with laws and phenomena you've prepared for. In that sense, knowledge is a companion. However, without careful mental discipline, the void could erode one's sanity. Sensory deprivation can lead to hallucinations. The brain might start creating voices or apparitions to fill the void. A lonely traveler might find themselves talking to imagined friends or sensing presences that aren't there as a way to cope. In literature and film, many isolated spacefarers converse with an AI or even an anthropomorphized ship's computer to meet their social needs. Perhaps one would talk to the stars as if they were old companions. Hello, Sirius. Bright again tonight I see. All of this underlines a truth. While the physical challenges of deep space are enormous, so are the psychological ones. On Earth, even in the quietest desert, there are distant sounds. There is a horizon. There are signs of life or weather. In deep space, none of that, only what you bring. Yet the human spirit is adaptable. If one approaches the void not with fear, but with reverence and curiosity, it might become not a prison, but a vast cathedral. Instead of feeling insignificant, one could flip the perspective. Yes, we are small, but we are here, a part of this grand universe, able to witness it. The silence isn't threatening. It's the backdrop for our own thoughts and for the subtle music of the spheres, like those gravitational waves or plasma hums we mentioned, which can be converted to sound if we choose. In this journey we're on, of course, we are together in imagination, you, the listener, and I, the narrator, accompanied by the knowledge inherited from generations. That alone is a comfort. We carry our civilization's collective experience with us, even into the void. Let's imagine our traveler finds a kind of equilibrium. They establish a routine, they record their observations, they find joy in small things, the taste of a recycled cup of tea, the act of reading a favorite novel by lamplight, the challenge of capturing a beautiful image of a distant galaxy with their ship's telescope. The mind can make a home even in the darkest places by finding purpose and beauty. Centuries hence, if humans, or our AI emissaries, go on interstellar or intergalactic voyages, they will carry not just equipment, but also art, memory, and philosophy to help them endure. Perhaps they will also have the comfort of communication with others making similar journeys. A community of the void, connected by faint signals or quantum communications, making the emptiness a little less lonely. As for us, on this imaginary voyage, we thankfully are not truly alone. We have the ability to return home in thought whenever we wish. And we have each other in sharing this narrative. Thus far, our journey has taken us from Earth's vicinity to intergalactic space. We confronted isolation and found meaning in it. Now, we will resume our exploration of outer physical realities, specifically some of the most extreme concentrations of mass and the grand flows of galaxies themselves. Armed with both scientific insight and a mindful heart, we turn now to one of the universe's most formidable and enigmatic denizens, the black hole. And after that, we'll look at the great attractor, a gravitational mystery on the scale of superclusters, before contemplating the fate of the universe and finally our place in it all. Take a deep breath. Our ship's life support has plenty of air. The journey continues, ever deeper into the dark, now toward one of the darkest destinations possible. The black hole, a well of darkness. From the quiet emptiness of intergalactic space, we set course for one of the most mind-bending destinations in the universe, a black hole. Specifically, let's journey to an isolated black hole drifting far from any galaxy, a rogue black hole, perhaps the remnant of a star that was flung out of its galaxy, or the merger remnant of two black holes that got a gravitational kick. This way, we can encounter it in relative solitude, without the blinding chaos of infalling matter, and appreciate the pure darkness of its nature. As we approach the coordinates, initially, there is nothing to see. Black holes, by their very nature, emit no light of their own, unless actively feeding on matter, which produces light outside the horizon. Our first hint that we're closing in is gravitational. Our ship's trajectory starts to deviate as if pulled by an invisible mass. Also, the pattern of background stars ahead of us begins to distort. Stars seem to stretch into arcs or smears, as if we're looking through a fisheye lens. This is gravitational lensing again, but cranked to maximum. The black hole's intense gravity is bending the light of background stars into rings and arcs as we move into the strong field region. We still haven't seen the black hole itself, but we see its shadow, a round patch of apparent emptiness where it blots out background light completely. Around that patch, depending on our angle, we might observe a thin photon ring, light from background stars that skim just around the hole and get bent into a circular path toward our eyes, making a faint ring of light outlining the darkness. We draw closer, cautiously. We won't cross the critical boundary known as the event horizon, as that is a one-way trip. Up ahead lies the ultimate dark region, the black hole's event horizon, a spherical surface within which no event can affect the outside universe. It's not a physical surface, but a boundary in space. Cross it, and even light cannot escape. To our eyes, it appears as a pitch-black sphere silhouetted against whatever starlight is behind it. In this case, since we are in intergalactic space, the backdrop is the distant tapestry of galaxies and maybe the glow of the Milky Way far behind. The black hole hides whatever falls behind that sphere from us, creating a black silhouette in the star field. Approaching fairly near but not too near, we begin to notice other relativistic effects. Time for us, relative to a distant observer, would slow noticeably. If we had a clock transmitting its tick rate to a faraway station, that station would see our clock ticks getting slower and slower as we neared the hole. Also, light from our ship to an outside observer would shift to redder wavelengths and dim, a process known as gravitational redshift. We, on board, might not feel anything unusual locally. Gravity is gravity, and as long as tidal forces aren't extreme, we could orbit a black hole much like we'd orbit any massive object, with the difference that we must keep a safe distance to avoid being captured irrevocably. Let's say this black hole is about 10 times the mass of our Sun, a typical stellar remnant black hole. Its horizon radius would be roughly 30 kilometers. That's a tiny radius compared to cosmic scales. meaning we can get fairly close within a few hundred kilometers and still be outside it. At that distance, the tidal forces, difference in gravity's pull between our ship's front and back, would be noticeable but not yet lethal. Closer in, they'd become very strong, potentially stretching objects, the infamous spaghettification. But we won't venture that close. Instead, we settle into a safe orbit, perhaps a few hundred kilometers out, engines firing gently to hold position. From here, the view is fantastically strange. Off to one side, we might see the normal star field of the universe. Off to the other, where the black hole is, we see that star field warped into a ring around a circular patch of pure black. If we look around the black hole, i.e., turn our camera as we orbit, we notice something mind-bending. We can see multiple images of the same background star at different positions. Light that passed on one side of the hole, or the other, reaches us from both sides. So a single distant galaxy might appear as two smears opposite each other around the hole. Some light may even be bent full circle. If we look toward the black hole's edge, we might catch a faint, delayed image of the very sky behind us, light that went around the hole and came back. In essence, the black hole's gravity is acting like an extreme lens and mirror, showing us around corners in space. There is almost no radiation here. We chose an isolated, quiet black hole. If it had nearby matter falling in, that matter would form a swirling accretion disk that would heat up and blaze with X-rays and visible light, potentially outshining whole galaxies. Indeed, the brightest persistent objects known, quasars, are accreting supermassive black holes in galactic centers, so black holes can paradoxically be sources of incredible light if there's fuel. But our black hole has no such meal at the moment, which allows us to appreciate the black hole itself. We're witnessing one of the darkest phenomena in nature in essentially its pure form. It's worth noting that in 2019, scientists produced the first actual image of a black hole's immediate vicinity, the one in galaxy M87, using radio telescopes. They saw a ring of emission surrounding the silhouette of the horizon, matching predictions of general relativity. In our case, we are getting a much closer, clearer view with our own eyes. It affirms what theory and that image told us. Black holes really do cast a shadow on the universe, a nearly perfect sphere of darkness. The environment just outside the event horizon is extreme. Space and time exchange roles in a sense. Falling toward the horizon is as unavoidable once inside as moving forward in time. If we were to send a probe toward the horizon, we'd see it approach that invisible boundary and appear to slow down, redshift, and fade, asymptotically freezing near the edge from our view. It would never quite disappear, just become increasingly dim and red until it's effectively gone. From the probe's own perspective, it would actually cross the horizon after a finite time and head to inevitable destruction at the central singularity, where density and curvature become infinite and our physics breaks down. But we, outside, are forever denied seeing anything actually enter. A kind of cosmic censorship that keeps the interior hidden. Hovering near a black hole like this, one might feel a mixture of fear and fascination. On one hand, this black pit represents oblivion, a one-way exit from our universe. On the other hand, it's a triumph of human understanding that we can predict and even visit, in theory, such a thing. We understand its radius, its mass, its effects. We know, for example, that over an incredibly long time, many orders of magnitude longer than the current age of the universe, even this black hole will evaporate via Hawking radiation, a quantum effect causing it to emit a faint glow and slowly lose mass. But that is trillions upon trillions of years in the future. At present, the hole's Hawking glow is negligible, on the order of nanokelvins, utterly undetectable. So, to us, it appears truly black. Let's consider a thought. Not all black holes are small. There are black holes millions or billions of times the sun's mass at galactic centers, with horizons as large as the solar system, If we were near one of those, the tidal forces at the horizon could be mild. They grow weaker relative to your size for bigger holes, so you could actually cross the horizon without spaghettifying immediately, only to meet your end later near the singularity. In our smaller black hole case, crossing the horizon would rip us apart quickly due to intense tidal forces. In either case, crossing is a no-return journey. For our narrative, we wisely keep a safe distance. We marvel at how this black hole, a place of maximal darkness, still announces its presence through gravity's influence. It reminds us that even where light cannot exist, the shape of space-time itself betrays the hidden mass. After orbiting a few times and collecting data, imagine capturing close-up images of the photon ring, measuring gravitational redshift of light signals, perhaps even dropping a clock in and watching its signals fade. Experiments that confirm again Einstein's predictions. We prepare to leave. We fire our engines and gradually spiral away from the black hole. The distorted star field slowly undistorts. The pinched ring of light around the hole smears and then breaks apart into normal star images as we retreat. The region of pitch black shrinks, and then suddenly the black hole becomes essentially invisible again against space, only detectable by the way background stars realign to their undistorted positions. We leave this well of darkness behind. It will continue drifting, perhaps eventually merging with another black hole, or gobbling some stray gas or star it encounters in eons hence. For now, it's a silent relic of a massive star's death, carrying a piece of the universe's mass in secret. Having confronted a black hole, arguably the darkest physical entity possible, we now turn to a different kind of darkness, one on a much larger scale. This isn't a single object, but rather a mysterious region toward which many galaxies, including ours, seem to be drifting. An expansive gravitational anomaly known as the Great Attractor. It's not an object like a black hole, not a single one anyway, but it represents a concentration of mass in the depths of intergalactic space that is largely unseen. It is, in effect, a dark hub drawing us and our galactic neighbors in. Let's set course toward the coordinates of the Great Attractor, a journey that will take us across tens of millions of light years and into the realm of large-scale structure and cosmic flow. The Great Attractor, the mysterious pull in the cosmic dark. No matter where we drift in our local supercluster, we notice something. Our galaxy, and many around us, are moving in a common direction, as if being gently pulled by the gravity of something massive ahead. This observation is at the heart of the Great Attractor mystery. In the late 1970s and 1980s, astronomers mapping the velocities of galaxies, after subtracting the general expansion of the universe, found a residual motion. The whole local group, Milky Way, Andromeda, and others, and even the Virgo cluster and other nearby clusters, appeared to be streaming toward a patch of sky in the constellation Centaurus. They couldn't see much in that direction. Unfortunately, the line of sight lies through the dense plain of our own Milky Way, where interstellar dust obscures distant galaxies. They poetically called this obstructing zone the zone of avoidance. Yet something beyond that galactic plane seemed to be tugging on us all, causing velocities on the order of several hundred kilometers per second towards that region. They dubbed the unseen mass concentration the Great Attractor, half in jest, half in awe, because whatever it was, it had the mass of perhaps tens of thousands of galaxies. What have we learned since? Later surveys, including X-ray surveys that can peer through dust, found that there is a large collection of galaxy clusters in that region, notably the Norma cluster, a massive cluster of galaxies hidden behind the Milky Way's stars, not easily visible in ordinary light, but detectable in X-rays and partially in radio-infrared. The combined mass of these clusters, plus their dark matter halos, accounts for a lot of the gravitational pull observed. In effect, the Great Attractor is not a single object, but a kind of gravitational valley in which our local supercluster, Laniakea, is situated, and towards whose center, the Norma cluster region, many groups and clusters, including Virgo and our local group, are flowing. It's as if we're all slowly sliding down the gentle slope of a very large gravitational hill. We, with our ship capable of traversing millions of light years in a reasonable time, imagination knows no bounds, decide to head toward this great attractor region to see what's there. As we travel tens of millions of light years, the Milky Way recedes into the distance behind us, joining the local group's other galaxies as just faint blurs. We enter a part of space more crowded with galaxies as we near the Great Attractors region. We might pass through the fringe of the Hydra Centaurus supercluster. Gradually, ahead, we see more galaxies clustering together. This is the Norma cluster, Abel 3627, very rich in galaxies. The space between galaxies here is still mostly dark, but punctuated frequently by fuzzy ellipticals and spirals drifting relatively close to each other. This cluster is enveloped in a huge cloud of hot gas, which we know from X-ray observations. Though we can't see X-rays with our eyes, if we had X-ray vision, the cluster would appear as a ball of faintly glowing plasma at tens of millions of degrees, filling the cluster and outweighing all the stars in the galaxies. And that gas itself sits in an even larger ball of dark matter that we cannot see at all except by its gravitational effect. So, in approaching the Great Attractor, we find that it's not a single thing like a black hole or massive planet. It's a convergence zone. Our entire region of the universe is in the process of slowly coalescing here. Over billions of years, our local group and others might merge into this cluster's outskirts, unless the accelerating expansion halts that. More on that soon. Standing at this location, say, on the outskirts of the Norma cluster, what do we observe? The night sky would be rich with galaxies. It would be like being near the center of a city, with city lights in every direction. Some galaxies in the cluster might be close enough together that their mutual light gives a faint illumination to intergalactic space, though extremely faint, still far, far darker than a starlit night on Earth. We would see giant elliptical galaxies bloated with stars, and perhaps active galaxies with jets from central black holes. This is a crowded dark. Space is still dark, but filled with more objects than we've seen since leaving the Milky Way. However, when we look out beyond this region, we notice something else. Even this Great Attractor region is not the end of the line. In fact, now astronomers realize that this area is being pulled towards an even larger concentration of mass farther away, known as the Shapley supercluster, a titanic collection of clusters, the most massive in our part of the universe, about 650 million light-years away. The Great Attractor was like a local valley, but Shapley is a deeper valley beyond, and even the Norma cluster and Great Attractor itself are being pulled in that direction. In truth, gravity's web extends hierarchically. Our cluster falls into a larger cluster complex, which may fall into a supercluster complex, and so on. But eventually, the accelerating expansion of the universe will likely stop these flows from carrying things too far. Our ship doesn't attempt to travel to Shapley. That's hundreds of millions of light years. We'll content ourselves with understanding it from here. We might, however, observe the motion of galaxies. We'd see the Norma cluster's galaxies engaged in a slow dance, some moving toward a common center. If we had the ability to mark positions and come back in a billion years, imagine leaving buoys in space and returning much later. We'd see progress, galaxies noticeably closer together, structures merged. The Great Attractor moniker, while a bit hyperbolic, gave a face to the idea that even in the darkness, there are currents. The universe has internal motions on huge scales, and we are part of one. It's humbling. Our Milky Way is racing at hundreds of kilometers per second due to these currents, yet here on Earth, we never noticed until we built instruments to measure Doppler shifts of distant galaxies. We're like a small boat drifting on a vast, slow-moving ocean current. Only by looking at the shoreline, distant quasars, can we tell we're moving. Let's take stock of where we are. We set out from Earth, left our solar system, passed through interstellar space, out of the galaxy, into intergalactic space. encountered a rogue planet, orbited a black hole, and now visited the heart of a massive cluster at the Great Attractor. We have traversed an enormous range of scales and phenomena. The darkness has taken many forms, from the simple absence of sunlight in interplanetary space, to the near-perfect vacuum between galaxies, to the ultimate darkness of a black hole's interior. We found that darkness is not uniform. Sometimes it's gentle and empty, other times it's dynamic and hiding immense forces. Our journey outward, in space, is nearly at its limit. The next step out would be to encompass the view of the entire observable universe, essentially to consider the cosmos as a whole. We can't physically travel outside our universe's observable bounds, but we can conceptually zoom out and talk about edges we cannot cross and the ultimate horizons in time and space. Before we do that, however, we have one more realm to explore, not spatial now, but temporal, the future. For there is a deep, dark space that awaits even if we never leave home, the far future of the universe, when starlight itself might cease. It's time to talk about light and time on the grandest scale, the cosmic horizon of what we can see, and the final fate of the silent vacuum itself. The eternal night, the destiny of an expanding universe. We have journeyed outward through space. Now let us journey forward through time. The subject is deep, dark space in the context of the far future. The fate of stars, galaxies, and the very fabric of the cosmos as expansion and entropy play out. This will be a speculative voyage, grounded in our best science, carrying us trillions upon trillions of years ahead to an era where darkness and emptiness may reign supreme. Right now, we live in what could be called the stelliferous era, the age of stars. Galaxies sparkle with billions of stars. New stars are still being born from gas clouds, and the night sky from any planet has points of starlight. But stars are not eternal. The larger ones burn out quickly, in a few million to a billion years. Sun-like stars live around 10 billion years. The smallest red dwarfs, however, sip their fuel so slowly they can last trillions of years, far longer than the universe's current age, which is almost 14 billion years. So, fast forward far beyond our current time. First, the massive bright stars will die off. We've already seen many of those go. In fact, in our Milky Way today, most supergiants are young and will explode within a few million years. In a few billion years, even sun-like stars, including our sun, will be ending their lives, swelling into red giants, then shedding into white dwarfs. But tiny red dwarfs will continue to burn their dim fires for a very long time. Imagine the universe at, say, 100 billion years from now, almost 10 times its current age. By then, most galaxies beyond our local group will have swept out of our observable range due to the accelerated expansion of space. The universe's expansion is carrying them away faster and faster. Future astronomers in our galaxy, or its merged remnant as the Milky Way is likely to merge with Andromeda long before that, might see an empty sky beyond their galaxy. No external galaxies visible because they've receded beyond the cosmic horizon. Only the galaxies of our local supercluster, now likely merged into one giant assemblage, would remain visible. The universe, from their perspective, would look static and lonely, a single island universe surrounded by infinite darkness. As time marches on, star formation in our giant merged galaxy will slow and eventually stop. The interstellar gas gets used up or locked in stellar remnants. The lights in the sky begin to go out one by one. In a few trillion years, the last new star will have formed. After that, it's a slow dusk on the universe. The existing stars, one by one, exhaust their fuel. The bright era of stars gives way to the degenerate era, dominated not by shining stars, but by stellar remnants, white dwarfs, cooling embers of sun-like stars, neutron stars, ultra-dense corpses of massive stars, and black holes. Also, planets that once orbited stars now find themselves wandering or clinging to cooling white dwarfs. The universe still has plenty of mass and objects, but almost none emit visible light. A white dwarf will glow from residual heat for many billions of years, gradually fading to become a black dwarf, a cold, dark sphere. Neutron stars might remain hot with stored heat for a long time too, but eventually they too cool, though neutron stars are so opaque and small that they become essentially invisible except perhaps via faint radio emissions, or if they were pulsars, but even pulsars slow down. At this point, the universe, perhaps tens of trillions of years from now, is lit mainly by the afterglow of white dwarfs turning to black dwarfs, and occasional accretion flares if two objects interact or collide. Starlight as we know it is essentially over. Future inhabitants, if any, might live on warm planets orbiting faint white or black dwarfs, eking out energy as best they can. Eventually, even those fade. It is a melancholy picture, darkness settling over the cosmos, like a grand theatre show ending and the lights of the stage gradually dimming until only the emergency exit sign, perhaps the occasional Hawking radiation flicker or proton decay flash, remains. As we push further forward in time, more exotic processes become important. If protons, the building blocks of atoms, are unstable, some theories suggest they might decay after an extremely long time, 10-30 years. Then over truly vast spans such as 10-100 years, even matter as such might disintegrate into radiation and elementary particles. If protons are stable, matter persists as iron lumps and such indefinitely. Regardless, gravitational dynamics continue. Stars and remnants will shuffle around, some getting ejected from galaxies, others merging into the central black hole. Ultimately, one expects a large fraction of mass ends up in black holes, since many stars will fall into them or merge to form them. So, in the far, far future, black holes might be the last bastions of mass. They too are not immortal. Through Hawking radiation, black holes slowly evaporate, a process unbelievably slow for big holes. A stellar mass black hole might take 10⁻⁶7 years to evaporate, a 1 with 67 zeros. Supermassive ones take far longer. The one in our galaxy would take around 10⁻⁹ years. But given enough time, even they will evaporate. So imagine, after hundreds of trillions of years, the last black dwarf star fades to darkness. After quintillions more, the last stellar black hole pops out of existence in a final burst of Hawking evaporation. What remains then? A thin gas of fundamental particles, electrons, positrons, neutrinos, photons, etc., at extremely low energies, sparsely scattered across ever-expanding space. This is the projected heat death of the universe, a state of maximum entropy where all energy is evenly spread and no gradients exist to do work. The temperature everywhere is effectively at the background minimum, which itself gets lower as expansion stretches the remaining photons to longer and longer wavelengths, approaching absolute zero from above. It is an eternal night so complete that, to any conceivable observer, nothing happens and nothing can be done. The cosmos has gone to sleep. Of course, this assumes our current understanding. Dark energy remains a constant vacuum energy, leading to accelerated expansion forever, and no new physics intervenes. There are alternative possibilities, e.g., a big rip in which dark energy's effect grows without bound and shreds even atoms in the far future. Very speculative, and current data suggests it won't happen. Or a cyclical universe, where after eons, a new Big Bang might be triggered. Also speculative without evidence as of now. Or the small but mind-bending chance of a vacuum decay, where what we call empty space is actually in a metastable state and could quantum tunnel to a lower energy state, creating a bubble of true vacuum that expands at nearly light speed and essentially destroys the universe as we know it. Again, speculative, but if it were possible, it could, in principle, happen at any time without warning. Cheery thought. There's also the concept of Boltzmann brains, that given enough time in a heat-dead universe, random fluctuations could produce a self-aware entity, a brain, out of the chaos, albeit fleetingly, due to sheer chance. But these are deeply theoretical musings, in the absence of anyone to observe them. In the scenario that most fits current evidence, eternal accelerated expansion, our universe ends not with a bang, but with a whimper, or rather, an endless sigh of dispersing energy. Let's pause and think what that means for meaning. It's a somber vision. All the brilliance and structure the cosmos developed, stars, galaxies, life, maybe intelligence, all eventually dissipates into nearly nothing. The legacy of the universe becomes essentially a very cold, dilute soup of particles and photons, expanding into an ever vaster emptiness. One can find this depressing, the ultimate futility of all structures. Or one can find it peaceful. The universe returns to a simple, quiet state after a tumultuous youth and middle age full of drama. In this far future, even black holes, those engines of destruction, have evaporated into gentle Hawking radiation. The darkness is truly and literally everywhere. If some incredibly advanced beings wanted to postpone this darkness, they'd have to find ways to gather energy or create new ordered pockets. But thermodynamics suggests they can't stave it off indefinitely. Eventually, usable energy runs out. As our journey to the future concludes, we imagine ourselves floating in that eternal night. We are now trillions upon trillions of years from our present time. The Milky Way, the great attractor, all of it is gone or quiet. Perhaps we see nothing with our eyes, no stars, not even the faint glow of a galaxy cluster. Only perhaps a thin haze if we amplify certain wavelengths, the dying embers of creation. It is an empty stage, but we recall the vivid scenes that played out on that stage in earlier eras. We, our distant descendants or thought experiments, carry the memory of a lively cosmos into this twilight. Perhaps we, or our far future proxies, could still find meaning as memory keepers, storytellers of the long-ago age of starlight. And here's a thought. Perhaps this isn't truly the end. Some cosmologists speculate that given infinite time, quantum fluctuations might eventually create new Big Bangs or new ordered regions, a kind of rebirth from the void. These ideas are speculative and often untestable, but who knows? The ultimate end might be a new beginning in ways we can't foresee, like the formation of a new universe in a bubble of the old. If the multiverse concept is true, perhaps new universes are being born elsewhere, even as ours dies. So the grand story never truly ends, but continues in other arenas. Be that as it may, from our perspective within our universe, heat death is as close to an eternity of darkness as we can imagine. Now gently, we return our attention to the present journey. We have seen the end of all things, scientifically speaking, and with it, the triumph of darkness. It leaves us with a profound appreciation for the time we live in, when the cosmos is still young and full of light and wonder. We also realize something beautiful. Even as the universe heads toward darkness, we are here now, evolved in time to witness the pageant of galaxies and to understand what we're seeing. If the universe must go dark, at least it birthed minds that could comprehend and feel awe at its glory. We are, in a sense, the universe's way of appreciating its own ephemeral beauty. On that note, let's step back from the future and come back to our place in the dark. We've traversed space and time beyond all ordinary limits. It's time to reflect on what this means for us, floating on a small planet in the habitable zone of an ordinary star, a star that will one day die as well. With all this knowledge of the abyss, how do we feel about our fragile oasis of life and light? Epilogue: The meaning of nothing, finding light in the dark. We end our journey much as it began, in silence and darkness. But now the darkness is no longer merely an absence. It is rich with history, structure, and meaning we've layered onto it. We set out to explore deep, dark space, the vast, invisible, silent regions beyond planets, stars, and galaxies, and we found that each void held its own lessons. We learned that what seems empty is often full of invisible connections, fields, forces, and perhaps flickers of quantum potential. We saw that darkness frames light. Without the enormous gulf of dark space, the stars would not stand out, nor have room to shine or orbit. The void is what allows structure to exist, giving contrast and space for things to move and evolve. We also confronted the ultimate dark, the eventual night that may fall over the cosmos itself. Rather than despair, this knowledge can instill a kind of poignant appreciation. We live in the springtime of the universe, when stars still burn and galaxies swim in a sea of light. It is by cosmic standards a fleeting era. How precious, then, is a sunrise, a burst of starlight, the sparkle of a nebula? These commonplace wonders are, on the grand timeline, temporary gifts. Standing here on our metaphorical observation deck at the end of our travels, let's imagine looking back at our home one more time. Our planet Earth, that pale blue dot, suspended in a sunbeam, to quote Carl Sagan, is uniquely blessed with the light and warmth of a nearby star. Against the cold backdrop of infinite space, it is a haven of life. Recognizing this fills us with both humility and reverence. As Sagan noted, on that mote of dust is everyone and everything we care about. When set against the cosmic dark, that small bright world is all the more special. It underscores our responsibility to cherish and protect our island of light. At the same time, knowing the vastness beyond, we might feel less frightened by it and more connected. We are made of atoms forged in ancient starfire, scattered through interstellar space and gathered by gravity into living beings. Thus, even the darkness between the stars is kin to us, for it carries the ashes of dead stars that became the seeds of life. We are children of both the light and the dark. And consider, in all the silent dark we traversed, the one thing that persisted was our own consciousness observing it. In the ultimate heat-death scenario, if there were no observers, the silence would be truly absolute. But as long as there's someone or something to marvel, to understand, to know the universe, then the dark has meaning. In a way, through us, the universe is no longer silent. We give it a voice. We've done so in this very journey by narrating the secrets of space. We, tiny, temporary beings, have used our minds to illuminate billions of years and billions of light years, to unveil the hidden harmonies of the cosmos. The French philosopher Pascal, gazing at the night sky, shuddered at the eternal silence of these infinite spaces. Yes, the cosmic void can seem unbearably indifferent, but perhaps we need not be terrified if we carry our own flame of understanding. Where Pascal felt dread, we can feel a solemn awe. The darkness is vast and indifferent, but we are not indifferent. We care, we wonder, we dream, and so we supply the cosmos with meaning. Throughout our expedition, whenever we encountered darkness, we found something to learn or admire. The empty interstellar expanses taught us about perseverance and scale. The rogue planet in darkness showed resilience. The black hole silhouette revealed nature's sublime extremes. The great attractor's hidden pull taught us about unseen influences, and the far future's gloom casts the present in a warm, golden light of appreciation. In the end, deep, dark space is not empty to us. It's full of context for our existence. It is the canvas on which the stars paint their light. It is the womb from which galaxies were born. Recall that in the beginning, the universe was dark until the first stars ignited. It is the quiet stage that allows the play of cosmic history to unfold. And when the play is over, it is the gentle night that falls, perhaps awaiting some new dawn beyond our knowing. Our journey comes to a close, back on the familiar shores of Earth. Step outside on a clear night and look up. The sky may appear as a dark dome with scattered stars, but now you carry within you the stories hidden in that darkness. The silence up there is not frightening. It is profound. You might even feel a sense of companionship with the dark. It has been with us from the beginning and will be with the universe at the end, a constant backdrop to all of existence. As you gaze at the stars, remember that the very photons hitting your eyes may have traversed light years of dark space to get here. Think of what they witnessed, perhaps passing rogue planets, or skimming a black hole, or simply traveling for ages alone. And now, at the end of their long journey, those particles of light trigger an awareness in your mind. In that moment, you are the universe witnessing itself, the darkness delivering messages to a conscious spark. In the quiet after this narration ends, we are left with a feeling, difficult to name, a mixture of wonder, humility, and connectedness. The deep, dark space that seemed so forbidding at first has revealed its treasures to us. It has also reflected us back at ourselves, showing how precious the fragile light of life is against the vast dark. Our voyage through the emptiness has thus been, in truth, a journey inward as much as outward. We set out to find what lies in the dark. We return with a clearer sense of who we are and how we fit into this beautiful, immense, and silently eloquent universe.